Hello everybody. So it's just gone 10 o'clock and we'll make a start. Thank you all for signing up and for your interest in the webinar. We'll get going in a minute. I just want to run through a few logistical things first, just to sort of work out how we're going to run the webinar. Because there's quite a lot of people who've been interested in the webinar and learning about vegan. We're doing this on YouTube, which just means I don't have as much scope for the interactivity that we might have had if we were doing this at a workshop at a conference. So I'm going to go through a few logistics first. Okay. So welcome everybody. My name is Gavin Simpson. I'm a research scientist at the Institute of Environmental Change and Society at the University of Regina in Saskatchewan in Canada. Thank you all for your interest in the webinar, and I hope over the next 2 hours you learn something about using vegan for doing multivariate data analysis and ordinations, or that if you already knew some of this stuff, that you're become familiar with how to do these things in vegan. So today we're going to be going through largely with me sort of talking. I won't be doing any live coding during this webinar, and we'll see how this goes. But the slide deck is up on the URL that you can see on the screen there, and everybody who signed up through Eventbrite will have got a link to those. Also, the sources for the slides are up on the GitHub website. That's linked there, and there's a link to the live stream. I'll put a link to the recording up there, and all of the sort of R Markdown sources for the slides are available as well. So if you want to know how I was doing something, all of the code is up there as well. I will be showing the code for the examples as we go along, or bits of it, so that you can create the figures. But there are some bits that are hidden. Okay. So in terms of the for questions and answer, what I'm going to do is I've posted to those people who are who signed up for the webinar. Will have got this link to a Google Doc. The Google Doc, they just type in questions. What I will do is I will sort of stop periodically through the webinar and try and answer some questions in the live stream. I won't be able to, if there are lots of questions, I won't be able to respond to all of them, but I will do my best to, and I will follow up on the website. I'll follow up on the website later. Okay, so here are the slides. Here's the link to the slide. Hopefully you've got them up and you're following them. Here is the link to the Google Doc and the link to the GitHub as well. This live stream is being recorded, and it's the first time I've done a live stream, so I'm not exactly sure what YouTube does with these things. So I've also got a local recording, and I'll put up whichever of those is the best source. You'll get an email about that if you signed up through the Eventbrite thing. If you didn't and you're watching this, then, or you didn't get those emails, then just go to the GitHub website, and I will and I'll post a link there later today. Okay. So in today's webinar, what I'm going to try and cover, and we've got quite a lot to cover in the space of just sort of under 2 hours now, is I'm going to try and cover some diversity metrics and some just simple things for computing diversity. Vegan has a lot of functionality for doing diversity, but there are lots of other add-on packages as well for R that do other kinds of diversity things as well. And so I'm really just going to be covering some of the things that vegan does in that section. I'll talk very briefly about dissimilarities. They largely come into play when we start talking about some of the distance-based ordination techniques, which we'll get to later on. And then the focus for today is really going to be on unconstrained ordination, where we're looking for patterns in the in one set of information, so like species abundances or some environmental data, and we just want to look at the main directions of variation, the main gradients of change in those variables. And so we'll look at several different, excuse me, we'll look at several different techniques, including principal components analysis, correspondence analysis, and then we'll look at two distance-based ones. I'll briefly go through principal coordinates analysis and then talk a little bit more about non-metric multidimensional scaling and some of the sort of helper tools that Vegan has available for doing NMDS in ways that have been recommended for ecologists. And then we'll cover some practical tips for working and plotting, with Vegan and plotting ordinations using the Vegan package. So there's going to be lots of examples in there just showing how to work with the graphics, and we'll see that it's a little bit more complicated than perhaps you might be familiar with some other tools for like using ggplot, for example, to create plots. Okay, and just a shout out for those of you, if this has piqued your interest by the end, and I haven't put you off by the end of the webinar today, on Thursday, on July 9th at the same time, 10 a.m. Regina time, I'm doing a more advanced version of this, a more advanced webinar on ecological data analysis using Vegan. And the focus there is very much going to be on constrained ordination, using permutation tests, and how we build those constrained ordination models using Vegan and the formula interface, and how we test those. And then we'll run through some examples of how to sort of tackle some sort of experimental data and some non-standard things. And time allowing, I will also cover things like Permanova and the multivariate dispersions, equivalent to those things, some of those distance-based methods in here as well. Okay, I'm just finishing putting the slides together for that, so that's why I can't say for certain that we'll cover the Permanova, but I hope to. And we'll do a lot of work on permutation testing as well, and trying to use the constrained permutation or the restricted permutation tests that Vegan has available through the permute package. Okay, so we'll begin. I'm just going to take 1 second just to make sure I've got the Google Doc up on my screen so I can see things as I go along. And just to remind you, if you are following along and you do have a question, please just type it into the Google Doc, and then I will do my best to answer either in the stream when I take a break, or after the stream I'll go back and answer some things. And some things I've already answered, and some things might come up as we're going along, and so it might get answered as we go. Okay. So the first topic is diversity. I'm going to do a quick brief run through here. So there are, there are lots of diversity measures. Vegan has quite good coverage for the sorts of diversity, the standard diversity metrics that you might use. Although, as I said, there are some sort of more recent developments in this area that are perhaps better served by other packages, and I won't specifically talk about them because I'm not so familiar with those. But there are sort of three popular diversity functions that Vegan has available. The first is the Shannon-Weaver diversity, or Shannon diversity, and that's this value h here. And what this is just Shannon entropy, basically. We're just summing up the proportions of each species I multiplied by the log of that proportion, and it's negated here. And this is a standard entropy measure that's used in lots of different fields, and I think was initially sort of developed for communications and understanding sort of telephony. In these formulas, S is species richness. It's the number of species. And if we've got logs, then if there's a B, I'm showing the base of the logs, and usually they are to the natural logarithms to base E, but you can use other logs in here, and log to base 2, for example, for doublings might be appropriate. D1 here is the Simpson's measure, which is 1 minus the sum of the squared proportions of the species. And then there's a similar metric called the inverse Simpson's, which is just 1 over the sum of those squared proportions. These are all sort of fairly similar measures. They tend to give the same sorts of answers, and I'm not going to go into too much detail about the actual techniques. I just want to show you how these things work in vegan. And hopefully you can see these on screen. They look large enough when I was doing it, but I hope they're coming through all right on the live stream. So we're just, if you want to follow along here, you need to load the vegan package, and I've forgotten to put that in the slide here, but we need to load it. So library vegan will do that. And then I'm assuming you have it installed. And then we're going to load, for this section, we're going to look at some data from the BCI data, Barrow-Caro Island data set. And the function that we need to use is the function called diversity. And you just give this a matrix or data frame of species abundances or counts. In the columns, you would have the abundances, and in the rows, those are the samples or the observations. And I'm just showing here the standard diversity, the default metric that you get when you use the diversity function is the Shannon diversity indice. If you want to change the diversity index or the metric, then you need to use the index argument, and you pass this a lowercase name of the diversity measure. And the other two that I mentioned, the Simpson and inverse Simpson. And so you get the Simpson metric using index equals Simpson in quotes. And if you want the inverse Simpson, then you need to pass inv Simpson as the index. And then there is another argument, well, there are some other arguments, but the one I've mentioned about the base or the base of the logarithms, then you can change that here. The default is to use natural logarithms in this function, but if you did want to change them to sort of log 2 units, then you can do that here. And I'm just showing the first 6. What this returns is just a vector of dissimilarity values. And the labels that you see over the top of each of these diversity measures, these labels that you see on top here, they will pick up the labels for the sample labels. So if there's any row names in your data frame, they'll pick those up. Okay. There are some other metrics. I already measured species richness, and species richness is really easy to compute, but and I'm showing that in the second code block here. Just down here, there's a simple way to calculate this. But vegan also contains this function called spec number, which if you give it the same kind of object, columns are going to have the species in, rows are going to have the samples, and in this case we're just showing these are species counts. Then the spec number function will return the number of species in each of the samples. Okay. And then a metric that often people are interested in, not just the diversity, which you can think of the diversity as being a sort of spread or a variance, a distribution of values around a mean. Then the evenness here sort of shows about the evenness of those values, how equitable the counts are. So if each species was present at the same abundance, then that would be a very even distribution. If the sample was dominated by one species and there was no other species in there, then that would be a very uneven distribution. The vegan doesn't have a specific function for computing evenness, but it's pretty easy to compute, or one measure of evenness, Peelu's evenness, J, is easy to compute. And J is just the Shannon Weaver diversity that we computed previously, and then we divide that by the log of the species number, so the log of the species richness. And so this will have problems, for example, if you have if you've got data and samples that don't have any observations at all in them, if they're all blank, that log will come out as a minus infinity. yeah. Anyway, you compute that, and then this will give you back p-lose evenness. And so if this is something that you're interested in computing, then p-lose evenness is a good metric to sort of look at the how even or how similar the abundances are across observations, whether the samples are dominated by one species or another. Okay. So a lot of these species indices it's been observed are all follow a sort of general form, and they follow this general form of Regnier's generalized entropy. And I'm showing you the formula for Regnier's generalized entropy here. And this looks sort of somewhat similar to the Shannon metric I mentioned earlier and things like that. It also looks quite similar to the calculation for a variance as well. It's similar, except it has a log in here. Okay, and this is a whole family of entropy functions, and the order of the entropy is given by this value a, which I'm showing as a subscript on some of these things, and sometimes it's up here as a power. Okay, and we can plug in different values for a. We could plug in say 0 or 1 or 2, for example, and then they will return different kinds of entropy measures, which match on to some of the diversity metrics that we've already seen. And Mark Hill also sort of looked at these, and Mark Hill preferred to refer to these numbers rather as in their exponents rather than on the entropy scale that Régnier had them. And so there are, for every Régnier entropy, there's a corresponding Hill's number. And you might have heard of things like Hill's N2, which is the effective number of occurrences of each species, for example, or the effective number of species in a in a sample, and they're just the exponents of these. They're just the exponents of the Régnier numbers. And so we can calculate these Régnier numbers using the Régnier function in R. And if you want to get a specific scale or a specific order of entropy, so these were the values that I talked about A on here. If you want to get a very specific value of the Régnier entropy, then you need to pass in the scales argument. So if you wanted, for example, people often use Hill's N2 as a diversity measure, and if you wanted to get Hill's N2, then you would have to pass in scales equals 2, and then this argument Hill equals true, and then that will just return the exponents of these things. You just exponentiate them. Okay. And so I'm showing here one way of calculating N2, or the equivalent Régnier entropy for these things. Okay. So just while I'm here, there's sort of a question about what is sort of entropy. I've only heard of it in chemistry. I think that's the same kind of idea as chemistry and elsewhere. It's a sort of measure of the information, and so there's not a lot of information contained in a sample that just contains all of one species and none of another, and very few others, for example, where there's lots of information if an observation contains lots of individuals from a range of types, or in this case species, and so they're just measuring that entropy, or the amount of disorder. Okay, because if all the information is stored in just one thing and just one number, then that's not a lot of information. You can encode that very easily, and that's what sort of Shannon was kind of looking at when he developed these things. Yeah, it's just a sort of a measure of the disorder of the system, and by disorder what we mean is the higher the entropy, the more disorder we have, i.e. the more diverse the system, i.e. there's more information in that system. We would need to use more bits of information to encode the information in the species there. And so that's, if we have all the different, if there's 100 species and they all have slightly different abundances, but they're all sort of roughly sort of similar to one another, then that's a lot of information. It's harder to encode. That has a higher entropy than a system that has just one species that is the most abundant, and then there are no other species, because then there's very little information there. Okay. Yeah. Okay. So, and then the Renyi function has another another use. If you provide it a matrix, so just and here I'm just subsetting BCI just to return 6 of the rows, because there are lots of samples here. But what the Renyi function does, if you don't pass it the scales, then by default it will actually evaluate a large number of scales. The scales are shown at the bottom of this plot on the x-axis of this plot. Sorry, yeah, down here. So these are the scales. So I asked for scale 2 last time when I was showing the Hills N2, for example. But there are lots of other scales. And the idea behind this this diagram is, in the one way that people thought about Renyi entropy and diversity, is that if one site has higher values for each of the Renyi orders, then that site is more diverse than another site. So it doesn't matter that, so I guess the idea is not that you're just more diverse on a single scale. The idea here is that you try to be diverse on a range of the scales, on most or all of these scales. Pardon me. So we can see here, for example, that site 3 in the lower middle panel is the most diverse of all of these things. And what this graph is showing, it's showing the median in the pink, and then it's showing the lower extreme and the upper extreme of all of the Renyi entropy values for the different orders across these 6 samples. And then in the dots, it's showing the Renyi entropy for that labeled site. So in the top right panel, for example, the dots refer to site 16. And we can see that in that case, that site is sort of more abundant than the average of these, or the median of these 6, but it isn't the most abundant. Okay, and site 3, for example, has higher Renyi entropies for some of the later scales, but it isn't quite so high into some of the earlier scales. Okay, now there've been some questions in the Google Doc about which of the Renyi entropies map on to different dissimilarities. I'll answer that question later, just for the interest of time. I'll answer that later. And the logs, David has asked, what are the logs in Renyi's entropy? They are just their logs to base E, so natural logs. And given that I now can't say Renyi properly, I think we should move on to the next bit and move on. Okay, so rarefaction. This is something that people often want to try to do, and in some cases there isn't a good solution to the problem of the fact that species richness and diversity can, species richness tends to increase with sampling effort, and diversity often can as well. And so the more effort that you put in, so the larger the number of things that you count, or the larger of area you survey, the more species you will tend to find. And that obviously means that differences in diversity or differences in richness between your samples might be purely due to effort. And so an early way of trying to account for this was to use rarefaction. And the idea here is that you try and use rarefaction. It gives the expected number of species rarefied from n to n individuals. So we start off with capital N. That's the number of individuals found in a particular sample, and now we want to only sample a smaller subset of them, lowercase n. So lowercase n. So let's say we sampled 100 individuals in sample 1 and 50 observations, or 50 individuals, sorry, in sample 2. Then we would want to rarefy the first sample down to the expected count if we just had 50 individuals, so that we have the same effective count. And so what I'm showing here, this is the expected number of species in a rarefied sample where we start off with capital N individuals and we want to rarefy it down to little n individuals. So it's just the sum over the number of species of this 1 minus qi, and qi then is this ratio of some binomial coefficients. And xi is just the count of species I. So it's just the difference between the number of individuals and the count for this particular species. And we're going to choose n, lowercase n of them, and we're dividing that, or just normalizing it, by how many times we could select n individuals, lowercase n individuals, out of uppercase n individuals. All right. So this sounds a little bit of a mouthful, but this does give you the expected count for any value lowercase n given a certain number of individuals that you actually sampled, and you're obviously sampling down to. We can do this using, or implement this using the rarefy function in vegan. And so what I'm showing on here now is we're just going to look at this, the BCI data, and I'm just calculating the row sums. So this is just the sums of the counts, and you can see that in each of the rows, this is the number of individuals that were observed for each species, and then I've summed that over the rows to get the number of individuals sampled in each site. And we're just taking the quantiles of these, so we can see the min and the max, and then the median at 50% and the interquartile range. And you can see that there's a large difference between these sample locations in terms of the number of individuals that were counted. And so if we wanted to rarefy them all back to the smallest count, which is 340 individuals, then we use the rarefy function. We pass it in our matrix of species abundances, or our data frame of species abundances, and then we want to tell it what we want to sample down to. And so if we want to, here I'm showing you how to sample down to the smallest sample size, which is 340 individuals. Okay, and then what's returned by the rarefy function is a vector of now the expected species abundances. Okay, so this is in each of the samples. Sorry, the effective species richness. Sorry, in each sample. Okay, and so this is the species richness in each sample, and those are the rarefied species richness down to 340 individuals. Okay, and if you want to get an idea about how species richness varies with the sample size, then this recurve function is quite useful just for sort of visualizing these things. And so what's shown here, when you pass it a matrix of species abundances, is that it actually works out what the expected number of species would be for each sample in the data set for a range of different sample sizes from 0 all the way up to the observed sample size. And so the individual sites then are the things that are labeled in these at the ends of the lines. Okay? And then the line traces out the expected expected number of species if you were to have sampled, say, 200 or 100 individuals. And then if you pass in the value to the sample argument, then here I'm showing this is for the smallest sample size that we had in the data set of 340 individuals. Then this line shows the expected number of individuals, where it cuts, each of the curves, that's the expected number of individuals. And so these vertical lines show the expected sort of species richness for each of the sites. Okay. So that's the last bit I wanted to talk about on rarefaction. I've just had, there's one question in the Google Doc about the Renyi entropy curves. So no, they're not showing, these are not really sort of showing error or what have you. There's no sort of estimation or uncertainty going on here. These are just the calculations. So if we just ignore the lines for the moment, what this panel is showing is here for sample 12, what the dots in this plot are showing, the dots here, this is the Renyi entropy, and this is the Renyi entropy at order 0, then order 0.25, 0.5, and so on, for these different orders of entropy, okay, for the Renyi entropy. And they're the Renyi entropy is calculated for site 12. Then the next panel shows them for site 21. Okay? And then the lines that are drawn on each panel, they're in pink, they're showing the median entropy values for each of the Renyi the orders. So this is the median over, in this case, these 6 samples. But if you passed in more rows from the data set, it would be the median over all of the plots. And then the dashed lines, they're showing the minimum and the maximum for the sample that you passed in. So this line down here, this is the minimum entropy value for each order across all 6 panels, and this is the maximum Renyi entropy across all 6 panels for the different orders. All right, so they're just showing the min, the median, and the max across the 6 observations here, and then the dots are the observed Renyi entropies for each individual sample. Okay. Right, so the next topic is going to be on dissimilarity. And for the interest of time, I'm going to move on, and I'll come back to some of the questions for diversity later if we do have time. Okay, so dissimilarity metrics, I'm only going to go into briefly. I could spend hours talking about this stuff, but because there are so many of these things, and there are so many of these different coefficients, and I just want to explain a few of them just to get the general idea across. So what I'm showing in this graph here is the way one way that we can calculate the dissimilarity between 2 observations. And so the observations, the samples here, are represented in the space of 2 variables. So we have variable 1 here, could be species A or B, and then we have variable 2 here. Okay. And this could be another species or another variable that we're measuring. Right? So we have these 2 variables that we've measured, and we have 2 observations or 2 samples. And this is sample, we'll call it sample 1, but sample J, doesn't matter. Okay. And then we have another sample up here. Right? And if we want to measure the distance or the dissimilarity, how different these 2 observations are from one another in terms of the 2 variables that we've measured, then one way to do that is just to measure the Euclidean distance or the Pythagorean distance between the 2 samples. So in this case, this is the length of this line that I'm showing here in this plot. Okay, and so we calculate that using the equation at the top of the page, at the top of the figure here. So we just calculate the difference. So this is the distance in this direction. So the distance between the 2 samples in terms of variable 1, and we calculate the distance between the 2 samples in terms of variable 2. We square those differences and add them together, okay? And then we take the square root, and that just gives you the Pythagorean distance, which is the length of this line here. Okay. And we can generalize this to more than just 2 dimensions. If we had 3 species, then this would just generalize. We would just calculate the difference between our observations on the 3rd dimension, square that difference and add it to the other differences, squared differences. Okay. And so the general formula for that is shown up here. This is the Euclidean distance equation. All right. And many metrics or dissimilarity coefficients look or have a form that's very similar to this. Okay, where we have some sum of the differences between our observations in terms of the kth variable or the kth species. So here there are k species, we've got k variables. So we're just looking at the squared differences between our observations xi and xj. We square those up, sum those squared differences, and take the square root, and that gives us our dissimilarity. And we can do that for as many species, as many variables, as many dimensions as we want. An alternative measure is the Manhattan distance, and this is what I'm showing in the next equation here. And graphically, what the Manhattan distance is, or the taxicab distance, is that instead of measuring it as the crow flies, this direct distance between the two samples, we can measure how far you would have to travel if you were moving along, say, city blocks in New York or what have you. All right, hence the taxicab distance. So if you wanted to get from I to J here, then you would have to go along the block here, and then so you're going west along the block, and then you turn north and you travel in this distance here. And so we want to know this distance that's drawn out by along these two lines. And we do that by taking, instead of taking the squared differences, we take the absolute differences. So the absolute difference in this direction, and we add it to the absolute difference in this direction, and that gives us the Manhattan or the taxi cab distance, and that's shown here. And these little vertical bars just mean to take the absolute value of the differences here, okay? Because it doesn't matter which, the reason we take the absolute value is it doesn't matter if we start over here and move this way, or whether we start over here and move that way, okay? But the form of this is the same, and we just sum up these absolute values. And so one thing we can see here is that if we were to square all these differences, then things that are big in abundance will tend to be, those species will dominate because they'll have a larger value for some variable, right? So if one species is really, really abundant, it will dominate this equation because we're squaring those differences, okay, in the species. So this sum will be dominated by the abundant taxa or the large values. Whereas and that's because if we square a big number, it goes really big, right? Here, if we take absolute values, then we're not squaring big numbers anymore. And so the rare things have less of an influence over this Manhattan metric. And then this bottom one here then is showing you the Bray-Curtis, quite popular. And it's actually the default in the dissimilarity function that I'm going to talk about in a minute. It's the default in vegan. And so you see at the top here, we have sort of the Manhattan metric, okay? And then we have just some standardization here, okay? And we're not taking the absolute values now, all right? But we're not squaring anything, again, in this one here. And so Bray-Curtis can be less influenced by these outlier observations, right? So there are lots of these different coefficients. If you want to know the formulas and the equations for them, then the vegan manual has lots of good information on that. And I'll show you the function now, and then you can sort of follow on from there. So there are two key functions for when working with dissimilarity in vegan. One of them is this function vegdist, and that's the thing that's actually going to compute the dissimilarity measures, right? And then the second function, which is called decostand, for doing standardizations. And I can't for the life of me remember why it's called deco, why the deco bit's there, but it's for sort of standardizing data. And there's lots of different kinds of transformations in there. Vegdist works very similarly. So if you've ever used the dist, D-I-S-T, dist function in base R, then vegdist works in the same sort of way. You give it a data frame or a matrix of values for your observations, and then it returns a special kind of object, which is a sort of compact representation of the dissimilarity matrix. So it's not going to store the full dissimilarity matrix because that would be redundant, because the lower triangle of the matrix is the same as the upper triangle of the matrix. And in a dissimilarity matrix, they're symmetric. And so we don't store all of that. And so it returns something that you can plug into any function that expects a dissimilarity object, a dist object. So vegdist works the same way. It just has a lot more coefficients for ecological sort of data. And the way vegdist works is you pass in the data set, and here I'm using a different data set now. I'm using this lichen data, and we'll spend a lot of time looking at the lichen data shortly. But if you want to get the equivalent of the dist function, then using the Euclidean distance, then you would you have to tell it that you want a particular distance coefficient, and here you do that using the method argument, okay? And you pass in your matrix or data frame as species abundances. The default is to use the Bray-Curtis distance, and so that's where the second line of code that I'm showing here, is would give you the Bray-Curtis distances. Okay, and then there are some other distances, though dissimilarities, that are widely used in ecology, and certainly have been recently, where they look like Euclidean distances, but they're just transformed in some way. And one of those is the Hellinger distance. And I'm going to use that quite a lot through this because it's a nice way of using principal components analysis to look at species data, so that we don't have some of the problems that correspondence analysis can have. And what this means is we can transform the data in some way so that when we take the Euclidean distances of them, we get back, in this case, the Hellinger distance, but it could be the chi-square distance. Okay. Which is another transformation that you can apply. So it has and that's the very similar to the sorts of dissimilarity that's preserved in correspondence analysis, for example. So you could transform your data, take the Euclidean distances of them, and then do a standard ordination like PCA, and that can get around some of the problems that correspondence analysis has. Right? So, and there are lots more transformations in DecoStand, and so I really do suggest that you go and have a look at them. We'll come across one of the other standardizations or transformations later when we look at NMDS, where we might apply the Wisconsin double transformation, and for one of the things that Meta MDS does, and that is runs the code that's in DecoStand. Okay, so I could spend the rest of this seminar talking about dissimilarities. They all have different properties. They all work in different ways. The ones that I've mentioned work fine for. I mean, you can use them on presence-absence data, but they're not necessarily great on presence-absence data. There are better coefficients to use there. And for the interest of time, I'd left off a slide on what sort of some of the binary coefficients for the presence-absence data. What I'll do after the webinar is I'll put that slide in showing some of the metrics that might be used for presence-absence data, like the Yakard similarity and so on. Okay, and yeah, but I could talk for hours on this sort of stuff. One other slide I will put in is something called Gowers distance, and Gowers distance can be used for mixed data. And so the version I think that we have in Vegan, I can't remember if it will do mixed data or if it just has the version for quantitative data. I think now there is a mixed version in there, but Gowers dissimilarity can work for continuous data, ordinal or categorical data, and presence-absence data, and they can be on a whole range, a mix of those variables. Okay, the coefficients that I've mentioned before are really more for sort of abundances or continuous values. The Gowers distance can handle all kinds of data, and if they're all mixed up in your data set, then Gowers is one of the few dissimilarity functions that will allow you to calculate a dissimilarity across all the variables. Okay, I'm going to leave the question about occupancy and have to think about that one. Okay. So the next topic is going to be ordination, and this is a sort of long topic, and I'm going to explain some of the different ordination methods and some of the ways that we fit them in Vegan, and then we'll go on to how we work with some of the diagrams. So I might not explain some bits of the code as we go along, but hopefully by the end you'll have a good idea of how to sort of do some of those ordination diagrams and things that I might have skipped over. Okay. So the word ordination comes from a German word Ordnung, which means to put things in order, essentially. The German word itself just means order. And that's really what we're trying to do with ordination. And I think in terms of the sorts of ordination techniques that I'm going to talk about today, we're very much just trying to create a mapping or an ordering of sites along gradients in such a way that we can try and explain patterns of variation within those, or sort of signal within the sort of noise of the data. And so in ordination, we try and arrange our samples along some gradients by fitting lines and planes through the data that try to describe the main patterns in those data. Or we might try to, rather than thinking about these latent gradients directly, we might just want to have a low dimensional mapping. So we might not really worry too much about what the gradients are. We might just want to have a low-dimensional mapping rather than trying to view everything in many dimensions, in 4 or 5, as many variables as we have dimensions. We might want to just sort of see the best sort of 2-dimensional mapping so that we can look at how similar our observations are to one another, how similar the variables are to one another. And we're going to cover techniques that do these two things now. And there are sort of 3 families of models. One of them is for where we have linear sorts of response models, where we think that the observations respond roughly linear along these gradients. And so these will be techniques that will be suitable for sorts of environmental data and things like that. And perhaps species with short gradient, where you've got species data but short gradients, where there's not a lot of species turnover. We'll look at some unimodal methods, or we'll look at a unimodal method, which is correspondence analysis. And that's useful where we think the species are going to respond non-linearly across our gradients, or if we have a presence-absence data, for example. And then there are some distance-based methods which really don't think about a response model at all, or if there is a response model, it's based on the dissimilarity coefficient that you're using. And so really they're just interested there in doing a mapping. Okay, so we're going to look at unconstrained techniques today. We'll look at constrained ordination techniques on Thursday if you signed up for that webinar. So what do we mean by unconstrained? Well, what we're going to do is we're going to look for the major patterns of variation in the data set. So these directions of variation or gradients that best separate our sites. And once we've found those, main gradients or directions of variation that best separate our sites or our samples, then we want to, as a secondary step, relate any measured environmental variables to those gradients, say through correlation or through vector fitting or whatever. And we'll look at how we do the vector fitting and things later on in the webinar. So this sort of contrasts with constrained ordination, or the canonical ordination methods, which we'll look at on Thursday, where in the constrained methods, we want to see we want to create mappings and ordinations and fine gradients that we can explain given our measured environmental variables. Whereas in the unconstrained stuff that we're going to talk about today, we don't care about whether we can explain those gradients or not. We just want to extract those latent gradients, these axes of directions of variation, and then we'll worry about how well we can explain them with the environment later, right? And these things are actually complementary techniques, and you probably want to do both. And vegan actually allows you to sort of do these combined analyses where you might fit a constrained method, but then look at the unconstrained components that haven't been explained by your measured environmental variables and look at those afterwards. And we'll maybe talk a little bit about that on Thursday. So the unconstrained methods answer the question of how well do we explain the main patterns in the species data, these directions or latent variables, whereas the constrained techniques that we'll talk about on Thursday, they answer the question, how large are the patterns that we can explain with the measured data, right? So the main ordination techniques that we're going to look at are principal components analysis. This is a linear method, so it fits lines and planes. It's most useful for environmental data, sometimes with species data that have short gradients, or if you apply a transformation, then so because the principal components analysis sort of preserves the Euclidean distance, if you transform your species data using that Hellinger transform, for example, then the ordination actually then is nonlinear in a sense. And so if you do a transformation, you can then apply a particular set of transformations, you can then apply PCA to it and get a good ordination, even though you've got these nonlinear species responses. But traditionally, PCA is a linear technique that's used for sort of environmental data and things like that. Correspondence analysis is the classical ordination technique that's used for species that respond non-linearly along gradients. It's a unimodal method. It's most useful for the species data, presence-absence data, things like that. But it can also be used when there are short gradients as well, and actually works surprisingly well no matter what data you throw at it. It just can't be negative for correspondence analysis. Okay, so it's really thinking about something that's abundance based or positive, yeah? Or presence absence zeros. And then we have principal coordinates analysis and non-metric multidimensional scaling. They can be used with any kind of data. The only real constraint is that you have a suitable dissimilarity metric for them. So if you've got a mixture of different data types, you could use principal coordinates analysis or non-metric multidimensional scaling, but you would have to use something like Gower's mixed coefficient to compute the dissimilarities first, and then you can use these two techniques to do the low dimensional mapping. And these techniques aren't really interested necessarily in finding these underlying gradients in the data. They work quite well, but they have this extra problem with them in that we don't really get the species information coming along with them because we've turned everything into dissimilarities to do the mapping. All right. So these are the techniques that we're going to go through, and I'm going to start off by looking at this PCA. Principal components analysis. So hopefully all of you are sort of familiar with regression and linear regression. We could, if we wanted to, we could look at our multivariate species data by trying to do a regression for each species, each response separately. And so we'd have a bunch of these models, and then we'd have to summarize them in some way. And if we had 100 species, then we'd have to have 100 regressions, and that would be unwieldy and a pain to do and very time consuming. Okay. So we're going to do something that's a bit like regression, okay, except now we're going to have no explanatory variables whatsoever. We just want to try and recover those explanatory variables, these latent or underlying gradients, from the data. So it is going to be a regression. We're going to do it with all of our species as a response variable, but we don't know what the explanatory or predictor variables are. Those are the things that we're going to try and uncover. All right. And if you think about regression, it's just a linear combination of variables. It's some coefficient, some weight, multiplied by the value of the variable. And then we add up the weighted version of the value for variable 1 with the weighted version of the value for variable 2, and so on. That is a linear combination, right? And we're going to try and uncover those weights for each of our variables that best separate our sites in some way, or best explain or best disperse our sites in some way. And so what PCA does is it fits lines and curves, lines and planes through the cloud of data in such a way that it maximizes the variance of the data captured by the line or by the plane. And another way of saying maximizes the variation of the data that's captured by the line is to just say it best spreads the points out along that line, or best spreads the sites, our samples out along the plane if we're fitting 2 dimensions, for example, 2 principal components. And it does so, it fits these lines and planes by minimizing the distance between the fitted line and the plane, the fitted line and the observation, so the distance between the line and our observations. And then we've fitted our first principal component through our data. So that's the one that is the line through the data set that maximizes the spread of our sites along it. Okay. Then we can fit a second principal component. But no, we don't want to just, we could just take that first principal component and shift it a little bit, right? And that would explain almost as much as the first principal component, but it's not explaining anything new. And so when we extract our second and higher PCA axes, we add a constraint, and that constraint is that the axes, as we extract the second axis, it has to be orthogonal or uncorrelated with the first axis. And then when we extract the third principal component, it has to be orthogonal or uncorrelated with the previous 2 axes. And in that way, each additional principal component that we extract from the data explains new information that isn't captured by those previous principal components. Okay. Now, I often like to say that principal components is just a rotation, and this slide actually comes from when I was giving a workshop in Australia, and so it's an Aussie rules football. I hope I've got the right name there. I get confused living in North America about whether it's soccer or football or what. But anyway, I think this is Aussie rules football. And I could take that ball and I could twist that ball in all sorts of directions to show you different bits of that ball. Okay? It's something that exists in 3 dimensions. It's got a length, a width, and a height. So I could rotate that around, but there would only be one view that I could show you that would show the sort of maximum amount of that ball. Right? And it would be something roughly what I'm showing you here, where you can see the first principal component would goes through the sort of long edge of the board of the ball, and then the second principal component is going up and down like this. Okay. Now normally I would try and do that visually with a ball, but I didn't actually have one here. I try and sort of show that visually. So I've got some figures and some animations that will hopefully explain this a little better. Okay. And so our first step here, what I'm showing is I've got 2 variables. So these are samples that essentially drawn from that ball, maybe. They're both Gaussian to make this easier, and so they form this sort of elliptical bivariate relationship. And you have these 2. I'm just showing for 2 dimensions, but this works in the same way for many dimensions. If we had 3, 4, 5, 6, as many species as you want, this idea works. Okay, so the way principal components works is we center the variables, or at least Vegan does. You can do this without centering, and Kanoko, for example, commercial software allows you to do non-centered PCA as a special type of technique. But most of the stuff that we're talking about here will use centering. All right. So we center the observations. What we mean by there is that we're going to subtract the mean from the mean of variable 1 from each value of variable 1, and we're going to subtract the mean for variable 2 from each observation of variable 2. Okay, and so what that does, it just shifts the origin of the plot, the 0, 0 points, to the center of the data, the centroid of the data. All right, and so I'm showing that now by putting these black lines on the plot as a new set of axes. Okay, and then what principal components is going to do is it's going to find the direction through the data that best spreads out the observations. And so we could sort of draw lines through this data. We could put a line through here. We could put a line through that goes through there. Okay, but those lines don't capture the largest direction of variation in the data set. The line that does capture the largest direction of variation is shown by this orange or yellowy line that's going up in this direction. Okay, and you can see that along this line, the sites are most spread out. The data points are most spread out. So the way to think about it then is you have to project a point down so it has an orthogonal or meets it at right angles, meets this line at right angles. So that's where the points project onto that new axis. It actually happens to be the first principal component. Okay, so this is the line that maximizes the variation of the data along that gradient, or maximizes the variance explained, okay, for this line. And we're always going to be thinking about these perpendicular distances. It's not like regression, where we fit these distances where we only have a distance in the y-axis here. No, we're going to have distances in both the x and y, so we have these orthogonal distances, so distances that are right angles to the lines that we fit. And that's because everything is a response variable. If we just did them as straight lines that drop down, so we had all the variation in the y-axis, okay, then that would be just saying that all the error, all the uncertainty is in this one variable here, x2, and there's no error in x1. And we don't want to do that. We want to treat all of our observations, all of our variables the same. We don't want to treat them in an asymmetric way. Okay, so that's why we're using these orthogonal distances. We measure the lack of fit in both x1 and x2, or in as many observations, as many variables as we have. Right. Now, once we've found this first axis, okay, we can find a second principal component, and that then has to go at right angles to this one. But it could be sort of pointing into and out of the page like this, right? As it happens, it's actually going in this direction, like this way. and that then spreads out the points the next most, okay? And in this instance, there are only two principal components because we've only got the two variables, all right? And then what we do, once we've found these two directions, when we find the directions in the original space, what we're going to do is we're going to rotate that space so that the first principal component becomes the x-axis, the second principal component becomes the y-axis, and if we had other principal components in our data sets, they would become the new axes in these higher dimensions. And that's what I'm showing at the end here. So now we've rotated our data, and really PCA is only a rotation. It's the rotation here is just in these two dimensions because we've only got two variables. But if in the case of the ball, it could be a rotation in three dimensions. And obviously when we've got a large amount of data with many species, then we're doing a rotation in that high dimensional space. But that's complicated to think about. But this is all that's happening here. And I now have a little animation that will sort of visualize this for you. Yeah. And so we just see this is just rotating the data. Okay, it's just rotating the data to those axes. So you find them in the original space, which is I should have made the animation a little faster. So you find them in the original space, which is there, and then you rotate the axes so that the first principal component becomes the horizontal axis, the second becomes the vertical axis, and so on. Okay, that's all the principal components is, really. Okay. So should have had this slide earlier. I apologize, but this is what we're doing if you want to follow on. We're going to load the vegan package, and for what we're going to do now, we're going to use the VerSpec, this lichen data, and it has some environmental data as well, and we're going to look at the environmental data after we've looked at the species data. Okay. Now vegan comes with a number of data sets, and I'm just going to use the lichen data now. We'll look at the Dune data later on. We've already looked at the BCI data. So there are quite a few data sets here that just are useful for working with it, and this just means you don't have to worry about loading any data yourselves for this point. Okay. So what do these data look like? Well, most of the functions in vegan, we've already seen them, but they take these data frames. A data frame is just like an Excel spreadsheet where you might have, we have your variables in the columns and the observations or the samples go in the rows. Here we have some labels. The labels might be in the first row and the first column of your Excel spreadsheet. These labels and the row and column labels here are not actually in the data frame. They're just the row and column names of the data frame. And so this is a data frame, and usually this is how if you get your data into R, this is how it will be. Or if you're using some of the tidyverse tools, it might be a more modern version of a data frame, but it works in roughly the same way, right? Each column is a variable, each row is an observation or a sample. Yeah. And this vegetation data from lichen pastures in Finland has 24 samples and 44 species. Okay, so this is when we're looking at the dimensions of the object. The first one is the rows. R thinks about rows first as the first dimension, then columns as the second dimension. So we have rows and columns. So we have 24 samples, 44 species. And I'm just showing you here just the first 6 species and the first 5 observations, right? So these are abundances. And I can't remember now exactly if these are percentage abundances or if there's been some transformation applied to them. But I can't remember now, unfortunately. Okay. And just those of you who might be using vegan or want to use vegan for things like OTU data or microbiome kinds of data, I know, having worked with some of those data, that the data files come to you and they're transposed. They don't look like this. They're in the other orientation because you might have so many, you might have thousands of OTUs. It can become problematic to put them in the columns because it'd be so wide. Those data sets will be transposed. They'll be the opposite of what's needed for vegan. So if you do load your data in, make sure you get them in this orientation where the OTUs would then be in the columns and the samples have to be in the rows. All right. But that's the main thing. And importantly, when we're doing ordination like this, often, relatively often, people will store the environmental data and the species data, because they're just other variables, in the same file. And that's fine. You might be doing a regression and you want to take the abundance of a species and then regress that with some environmental variables from the same data frame. That's fine in regression, because we can use the formula to work all of that out. Because we're trying to look at the relationships between a matrix or a data frame of observations with vegan, you need to be able to have your species and your environment separated in some way, all right? And so just bear that in mind, that if you do have all of your data, species and environment, in the one data frame, when you load it in, just make sure you subset it and select only the species and put them into a species data frame, and then have your environmental data in its own data frame. Okay. You don't have to store them on disk like that, but okay. Okay, and so this is the chemistry that's associated with it. These are all continuous variables, different. This is soil chemistry, so lots of different ion values. And then bare soil is the estimated cover for the bare soil, and hum depth is the humus layer in the soil. Okay, so we have that environmental data that comes along with it, and we are just going to look at the species data first and find the main patterns in those species data. So before we do that, and there's been a couple of questions about PCA. So one of the questions here is asking about, is there a rule of thumb for transforming environmental data prior to PCA? So what is the difference between transforming the data in a given method and centering and scaling? Okay, so centering and scaling. So centering is where you just, we've already seen that in PCA, where you center the values, you just subtract the mean for variable 1 from all the observations for variable 1, and you do that for each variable. That centers the data. It puts the middle of the data set, it puts the origin at the middle. Okay, and scaling then gives the observations, or the variables, unit variance. So they have variance 1. So if we're going to do a PCA, usually you'll want to center and standardize your environmental data, because otherwise, if you think about the variances, if you've got something that's measured in big numbers, then if something's measured in really big numbers and something's measured in really, really small numbers, if you just have a line that explains most of the big number, the thing that's measured in big units, that will, the ordination will look to find or explain variation in the variable with big numbers, and it will ignore the it will ignore the variable with small numbers. Okay, so in that case, you might want to standardize the data, and that just gives everything the same variance 1. And then what we're doing in PCA is actually looking at doing a principal components analysis of the correlation matrix. And so really, rather than looking at the covariances, you're looking at the correlations then. Okay. Now that doesn't change the distribution. All it does is just shifts them around and standardizes the spread, but the spread remains symmetric when you do that centering and standardizing. And when you center, all you're doing is just shifting the middle around, right? So you're not changing the distribution of the data. If your variables and environmental data are often like this, that because they can't, if you're measuring concentrations of things, or the depth or the size or the volume of something, those things can't be negative. So they have sort of weird mean variance relationships, and often they have very little variance at small values and larger variances as you increase those values, as the numbers get bigger. And that means that you tend to have outliers, and those observations tend to be skewed in their distribution. They have a long right tail. And that's where you might want to use something like a square root or a log transformation to try and make that the distribution of the observations more normal or more symmetric, right? Now, there's no real assumptions in PCA about that, but it's going to work best if you don't have observations that are just really extreme outliers on some of the variables, because what PCA will do is it will just tell you that that's a site's an outlier. Okay, so in the same way in regression, when you transform your predictor variables in regression to give them make them look a bit more symmetric, spread the values out, you can do the same thing to your observations here. If you're going to do that, then you want to do the transformation before you do any centering and scaling. And the centering and scaling is actually built into the PCA in vegan. So you're forced to do your transformation first. If you do the transformation afterwards, then because you'd have negative values, you wouldn't be able to take logs and stuff like that. So you transform the shape of the distribution first, then center and scale. Okay. I don't actually know what I kind of know what varimax rotation is, and I won't talk about that now. Jason, I'll answer that question maybe in the doc afterwards. Okay. So this is our chemistry. We're going to look at the species data first, and in vegan, PCA is just the unconstrained form of a thing called redundancy analysis, or RDA. And so we don't have a separate function for PCA. Just because it's an extra function, it would be an extra function to maintain. Sometimes I wonder whether we should write one, but we've never got round to it. And so you're going to use the RDA function to do this. But as long as you don't give it any explanatory or predictor variables, then it doesn't. You will just get PCA. All right. So you give it this data frame of observations with one or more variables, and then there's really only one more thing you need to do. And that's decide whether you want to scale them. And just as I said about this means give them unit variance, so make them all have the same variance. Something that you might want to do with your species data is to transform them. So even though those things are measured in the same units, they're abundances of things. If you've got some species that are very abundant and some rare species, then PCA will focus on the abundant things. It's what it's designed to do. Because it's working in those squared values, so it'll find directions of variation in the most abundant things. So they will get expressed on the first few axes. The rare species will be on the later axes, or their importance. And if you don't want that, you can give all species the same variance, and then what we're looking at is the correlations between the species now when we do our ordination, and not the covariances, and therefore we treat all species the same way and just look at the correlations between them. And so what I'm doing here is I'm actually doing two things. I'm standardizing my data with scale equals true. So I'm giving them unit variance. We automatically standardize, and that's we automatically center. I've standardized by setting scale equals true here. And that's what you should probably almost always do if you're looking at environmental data here. And then because I've got species data, I'm actually going to apply that Hellinger transformation. And so now this actually will give us a really nice ordination for the species data, even if these species data are sort of measured over they're having nonlinear responses to the gradients. Okay. So when we do that, we're going to store the output, and I'm being cheeky here. I said we probably should have had a PCA function. I'm just going to name the objects, the ordination objects that I'm creating, after the name of the method that we used. So here I'm naming it PCA. Okay. Yeah, I wouldn't normally do that in daily life, but I'm just doing that so that we can keep track of things as we go along. Right. If you type the name of the object then, then what you are getting here then is just some simple printed output. Okay. And so we get the call. So this is just a reminder of how you fitted the RDA. And then we get the same output for for correspondence analysis as well. So we have this column that's indicated by inertia, and we have the total inertia, so that's the measure of the total variance, and then we have the unconstrained, so this is how much variance has been explained by or how much has been explained by our ordination axes. Okay, so we have 23 of them, right? So it's just one less than the number of variables in this case, right? And it says here inertia is correlations. It's actually not variances. Sorry, I misspoke. It's correlations because we did scale equals true. All right. So it's the inertia is the correlations. And so we had 44 variables, 44 species. So there are the total sort of variation or variability in the data is 44 units. Right. If we hadn't done scale equals true, this number would not be 44. But we'd still see the total variance in the data set. Okay? And then what we get is a quick summary of the eigenvalues. And the eigenvalues just measure the amount of variance, or in this case, the sort of amount of correlation that's explained by each of the axes. And by definition, the first axis, the first principal component, has to explain the largest amount of variation in the data. And then the remaining components explain smaller and smaller amounts, right? And we just show the first 8 here. And usually you're typically going to only be looking at the first 2 or 3 of these things in general, okay? But we'll come on to that a little later. How do you choose them? Okay. So that was PCA of the correlation matrix, because we did scale equals true. You can do PCA of, and this is the default PCA of the covariance matrix. This is where the units of these things matter. And we do that by setting scale equals false, right? And when you do that, the call is almost the same and the default. So you don't actually even need to put this on here, okay, but it's the default. But the output that you get is almost the same, except now we have much less variance. Okay, so this is measured in actual variance units now in the transform data. Okay, but still the eigenvalues are now units. If you were to sum up all of these eigenvalues, all 23 of these eigenvalues, of which we're only showing 8, then they would sum up to this total value in here. Okay. Now, note, those of you who are familiar with Kanoko and have used that before, Kanoko scales things slightly differently. It always makes in PCA, it makes the eigenvalues sum to 1. Vegan doesn't do that, all right? But it's easy to get out numbers that look similarly. So in Kanoko, you can interpret the principal component, the eigenvalues, in terms of like a proportion of variance explained. You can't do that with Vegan, but there are ways to get that information out, and we'll talk about that in a minute. Okay. So having fitted the ordination, there's not really much else you can do with the numbers here, other than look at how many dimensions you want to plot. So the next thing to do is to plot them. You could just use the plot function, but typically for species data of the variables in PCA, it could be variable, it could be species, it could be your environmental data. Though we represent the species scores as arrows, as biplot arrows, and this is what I'm showing on this here. So the default plot in Vegan will just show them as points. It'll just put the labels, the names on the plot. But we want to perhaps have that more traditional representation. Okay. So this is a biplot, and the arrows here for the species are pointing in increasing abundance for those for each of the species that are named, and then the dots on here, these are the samples. Okay, so these are the coordinates, or where they map in both of the first and the second axes. Right? And we just get this default plot. I'm not saying this plot is pretty, and we'll look at ways that you can improve this later, but the biplot function, given the PCA object we created, and then here's something else we will look at later. You want to choose the function, the scaling that you apply. And this just is essentially is just sort of saying it controls how we really interpret these graphs. And here I'm just doing a compromise scaling, a symmetric scaling that actually scales both the species and the sites. Okay? But we'll talk about what the different scalings mean in a minute. Okay? So that's it. Now we can visualize things. All right. So let's have a look at what these plots actually show. Well, sample or species, the points on here, the black numbers. Vegan will, if you've got a lot of samples, it'll draw them as points and won't label them. Here it's just, if you have a few samples, it has labeled them. So we want to look, what it's showing is, it's representing, and because of the scaling that I've used here, this is not exactly true, but in general, points that are closer together are similar in terms of their species compositions. So sites, what's this, 27 and 28, they are quite similar in terms of their species composition, but site 23 up here and site 21 are quite different in terms of their species composition. And species that are samples that lie over on this side of the plot will tend to have species found there that don't, or either aren't found or are at low abundances to the species that are found in these sides of the plot here, and likewise in this direction. Right? The angles between the species, in this plot they actually approximate the correlations, but if you were to focus and use scaling equals species, then the angles between the arrows on the species would show their correlations between the species, so which species tended to co-occur together. Okay? And the length of the variables, the length of the arrows on here is a measure of the strength of those correlations with the different axes, right? And it's an approximation here because I've done symmetric scaling, but if you were to look at other scalings, then if you were to look at other scalings, then the correlations would be exact. Okay. Sorry, I'm just scrolling around in my notes. Okay. And we'll talk about scalings again in a second. Okay. So I mentioned the eigenvalues. We can use the eigenvalues to decide how many axes we really want to interpret. And a lot of effort has been spent trying to find sort of ways to look at the important axes here by doing some statistics or some calculations on the eigenvalues. But simple methods tend to work just fine, and usually we're just looking at the first two axes anyway. And so what you can do is you can draw a scree plot of the eigenvalues. And so what I'm showing here using the scree plot function in vegan is we're just in the black line here, we're showing the scree plot of the eigenvalues. And what we want to look for here is a change in slope. So a drastic change in slope, because a scree slope tends to have like a steep slope, and then it has a more shallower slope down here. And where you see that elbow in the plot, and it's not that well defined actually in this particular plot, but where you see the elbow, that could be an indication of where to stop. So in this one here, you would stop by just sort of showing the first two axes, for example. Okay. There's something else that you can do, and that's to compare it with a broken stick distribution, and that's what's shown in the red line here. The broken stick distribution is kind of like the null distribution. If I was just to randomly break, let's say I have a stick, and that stick has the same variance as the total variance in this data set, and I just randomly broke that stick into chunks and ordered them from the biggest chunk to the smallest chunk, then those chunks would explain a certain amount of variance in them, all right? But this would just be doing it at random, where there wasn't any structure to the size of those sticks, i.e. to the lengths of the axes. And so what you can do is you could say, well, at what point do my eigenvalues remain above the broken stick? And so that again in this particular data set is about here, right? And then you will find, just to random variation, some of these later axes will just bounce around a little bit, but they're roughly following the null distribution or the broken stick distribution. Here we clearly see that the first two axes explain as much, if not, they explain more variance than you would have under the broken stick if you combined them. And so we would just look at the two axes. So that's another way that you can do this, using the broken stick distribution. Okay. But otherwise, I mean, usually people will just look at the first two axes anyway. Maybe if you want to do a bit more plotting, you would look at the third. But then you've got more plots to do, because you've got to look at the first and the third and the second and the third and so on, because we can only really draw two-dimensional diagrams easily. Right? If you wanted to look at the summary of the eigenvalues, you get a lot more information out. And so, and here you can extract the eigenvalues using the eigenvals function, and I'm just showing here the first 5 of them. The scree plot shows, I think by default, 10 of them. We can also apply the summary function or the summary method to the eigenvals function, and then we get out the sort of information that you might be familiar with say Kanoko or whatever, where we get the eigenvalues, we get the proportion of variance explained, and then we get the cumulative proportion of the variance explained. So we can see here that there's about 20% of variation explained on axis 1, about 12% on axis 2, and in total they explain about 31% of the variation, and so on. Okay, and then when we get through to our last axis here, then there is they explain 100% of the variation, because we can extract 23 axes from this data set. Okay, so the summary method just provides a little bit of extra information that might be useful for you, so you don't have to calculate the proportions of variance yourself. Okay. I'm just going to look at some of the questions before we move on. So someone's asking, what is the difference of using the variance matrix or the covariance matrix? Well, you can look at the variance of an observation with itself, and that would be its variance, okay? And that's, well, I said that wrong. Anyway, you can look at the variance of each variable, but if you look at the variances of each variable in a set of variables and you look at the relationship between them, those are the covariances. And because we're passing in a matrix, we're going to do the analysis on the covariance matrix. So we can think about that we're doing the PCA on that covariance matrix, but then we look at directions of variation with them, in them. We're not really doing a variance matrix or anything like that. So it's the covariance matrix. If you use scale equals true, then you're not doing the covariance matrix, you're using the correlation matrix. Someone's asked why species and variables. So what I'm showing here is it gets a bit complicated and sometimes I just slip into habit. I'm an ecologist, so I tend to use species, but I realize that not everyone does that and it doesn't make sense if you've got environmental data. So just to be clear, what we're doing here with PCA is we have a matrix of variables. They are in the columns, it just happen to be species data, but we could have done a PCA of the chemistry that I showed. And that would be the same. The variables would be the different soil properties. The rows would be the samples, right? So I'm just going to use, I'll slip into it, I apologize, but samples and variables, and I'll say samples for the rows or sites for the rows, and then we'll have species and variables for the columns. It'll slip into it, okay? Okay, I'll talk about NFIT and ordisurf later. Does unimodal necessarily mean normally distributed? No, unimodal just means that there is a single peak somewhere, yeah. So it just has a single peak. Technically, in correspondence analysis, the method makes some other assumptions and that they're just unimodal, but I'll show you a picture of that. And what does it mean if you have negative eigenvalues? You can't get negative eigenvalues with PCA. We'll talk about negative eigenvalues for principal components analysis later. Okay. So the next thing to look at is correspondence analysis. I think my formatting has gone a little bit long, but we'll fix that. Okay, correspondence analysis. So correspondence analysis is very similar to PCA. In fact, it's actually just a weighted form of PCA. We use the row and column sums to weight the data, to weight the abundances, and then we essentially apply the same steps that PCA does, but now it's a weighted form. And that weighting has the effect of turning the analysis into one of relative composition. So we're not focusing on the absolute values anymore, we're focusing on the relative composition. And this weighting is actually a trick that's used all over the place to get linear-based software to actually fit nonlinear responses. It's just that this weighting trick also turns out to give you, if you do PCA with this weighted thing, gives you a correspondence analysis. Okay. Now, what correspondence analysis is assuming for its response model is that we have nonlinear responses. These nonlinear responses are assumed to be unimodal Gaussian curves that have equal height and tolerance widths and are equally spaced optima. We call this a species packing model from sort of theory, and this is what it looks like. Okay, so we're making an assumption that our species are incredibly nicely behaved along these gradients, that they have these symmetric response curves, they all have the same maximum abundance, that their optima are equally spaced along the ordination axis, and so on. And if our data did look like that, then correspondence analysis would actually give us a very close approximation to a thing called canonical Gaussian ordination, which would be the proper maximum likelihood kind of solution to this problem, where we assume that the curves are these Gaussian unimodal curves. Now, I mean Gaussian in the sense of like a Gaussian response curve, not necessarily a Gaussian distribution. Okay. Okay. But okay, I mean, our species are never going to behave so nicely as that. Okay. It's not very realistic, that species packing model. But actually, correspondence analysis turns out to be surprisingly robust at times to violations of this assumption, right? And we can use it for a lot of things. The main area where it really falls down is if you have these very odd observations, and then outliers can dominate the diagram, and so you end up getting this outlier pulled way off over here, and then it doesn't really do much for it, and you can't really do anything about it. Another problem that it can have is you can get the arch effect, and that's usually where you've got a very long gradient, a single long gradient, and there's no real sort of strong secondary gradient. And what happens is that this gradient that you see on the screen here gets folded in half, and then now because it's folded in half, it's actually orthogonal to what I'm showing on that screen there. And so then it gets selected as the second axis, and it creates an arch configuration in the diagram. And beyond that, correspondence analysis actually can do quite well. And if you get the arch, then one of the best things to do is just go and switch to PCA and use one of those transformations I mentioned. So correspondence analysis, we said, is this weighted form, has this underlying species packing model. It's not very realistic, but it actually works surprisingly well in many cases. Okay, so again, we have these two sets of site scores. We have the species scores and we have the site scores, and we're going to represent them in a biplot. The default way to do this is use the plot function. And just like we had to actually fit this, just like we did with using the RDA function to get PCA, correspondence analysis is actually the unconstrained form of canonical correspondence analysis. That's why we use the CCA function. All right. You just give it the matrix of your species abundances or your presence-absence data, for example. These can't be negative, right? Doesn't make any sense to be negative here for CA. So these have to be 0 or positive. Okay, and then once you've done that, you could print out the CA object and you get some indication of the eigenvalues. And I'm not going to go through that again because we've already seen that. I want to focus a little bit more on these plots. So what we've got here is a correspondence analysis plot or biplot of the data, and here we're just using the default one, which is the scaling, and I know for the life of me I can't remember what the default scaling is. Scaling equals the species scaling is what's being shown here. Scaling equals 1. Okay, and so in here we because this is species scaling, we're actually best representing the relationships between the species. So these now are drawn at the points, or these the labels are drawn at the species optima, and their abundance declines equally in all directions, these concentric circles. As you move away from that point in any direction, the abundance of that species is going to decrease. Okay? Because this is focusing on the species, the relationships between the sites that we're showing on the axes here, these points, they aren't that well preserved, and so they're approximating the distance between them. Okay, so I think it actually approximates the Mahalanobis distance between the points. It's not the chi-square distance between the points in terms of their composition. If we were to focus on the sites and do scaling equals sites, then we would be preserving the chi-square distance between these ones here. But then we wouldn't be best representing the species scores, all right? But basically, if your points are close together here, the general interpretation is that they have those sites have very similar species composition. If your site points are located very far away, then they will have quite different species composition, especially if they lie on opposite sides of the diagram. It's highly likely that these sites up here will have these species in them, okay, that are closest to them, and that these sites down here are unlikely to have these species in them, or they might have those species in but at very low abundances. All right. So the main difference here is that we don't represent the species by arrows really in these correspondence analysis plots, okay, because their abundance now is these unimodal curves, so these values are going to decline in all directions. And so we can see the effect of showing the different scalings on this plot here, on these 3 plots. So this was the default one that we just saw, which was this focusing on the species. Okay, or we can focus on the sites, or we can do some sort of symmetric scaling. In the first one, if we focus on the species, like I said, this best represents the chi-square distances in terms of the species compositions. So which species tend to co-occur together? This best represented here by the chi-square distances. So the distance on the plot represents the chi-square distance between the species points. When we focus on the site scores, now we're best reflecting the chi-square distance in terms of the composition between the samples. Okay, and the relationship between the species is now approximate. right? And then here I'm just showing the symmetric scaling. This actually is an approximation for both bits, but it's kind of doing the best approximation to show both bits of information with the least distortion, okay? But if you really want to focus on the species or the sites, then you would choose one of these two other scalings, okay? Why not? Someone's asking why not a DCA for the arch effect. DCA is one of the, I just find it an abhorrent method. It's doing some very, very weird stuff to your data. And that can just introduce further artifacts like a trumpet or a diamond configuration. You've probably seen these. And really the arch is often telling you something about your data, and you probably shouldn't be detrending it away usually. So I've often found that a much better solution for me is to transform my data like using the Hellinger transformation or a chi-square transformation, and then and then transform the data using one of those two transformations, and then do PCA. And in fact, you can do a chi-square transformation using the decostant function, and then take Euclidean distances of that transformed data, or do principal components analysis of that transformed data, and you'll get an ordination that would look very similar to what you would get with the correspondence analysis. It's not the same, but it's very similar. But it won't have the same problem of this artificial arch showing up. And so you don't really have to need DCA. If you do just have this single strong gradient in your data, all ordination techniques are going to sort of show some curve structure. And that's just because of what we're trying to do. This long gradient is actually sort of spiraling away in high dimensions, and you're just looking at this squished down version of it. And so it's a bit, there's not much you can often do about that if there's just a single long gradient. There are some techniques like, for example, principal curves is a technique that's been proposed by Glenn Diath to sort of deal with that kind of data. Okay, so we're going to move on. We're running a little bit behind time, so I'm going to speed up a little bit. We're going to look at some vegan basics now, and then look at some of the functions that vegan does to work with these ordinations that we have been we just looked at. So we're going to look at them in a little bit more detail. So as I said, the majority of vegan's functions work with a single vector, or more commonly an entire data frame where we have multiple vectors stored as the columns. So these measurements of these species, abundances, or variables. Okay, so the data frame may contain the species abundances, or it contain the environmental data. And for the purposes of today, where we are looking at the unconstrained ordinations, then if we have other data set, other information like the soils data from the lichen pasture data, we require those as two separate data frames, and I've mentioned that. Okay, so if we have environmental constraints that we want to include in a CCA, which we'll talk about on Thursday, you need to have those things separated into separate data sets, just like we have here with the lichen data. Now, it's not a problem, as I said, if you have these variables all in one data frame when you load it in. Just remember, before you start doing your ordination, you want to separate them out into two. So let's assume that you have a data frame called all my data. The first 20 columns of that are going to be the species data. So I'm just going to subset them out into a species data frame that I'm calling SPA here. And then columns 21 through 26, for example, of my original data frame might contain my environmental variables. I'm just going to pull them out into a separate data frame here called env. And then I would use SPA and env when I'm doing my ordinations, rather than having them all together. Okay. The other thing to remember is you really don't want to, when you read your data in, make sure that any labels are in the first row and the first column, and that they are not stored as variables in the data frame. This is a common mistake that people make. Make sure they are read in, and they are the row names and the column names of the data frame. Okay, but as long as you follow those few steps, you should be good. Okay. All right. When we're drawing our ordination techniques, we display two or more sets of data, and we actually can't display both the information about the species and the information about the sites, the variables in the sites, perfectly in the same biplot. We can't maintain all of the properties of those sets of scores if we try and represent the two things together. Okay. So our solution is to scale one set of scores relative to another, and we do that using the scaling argument. So this is how we scale them. Now I put this in here for reference because this is how you might see it in Pierre Legendre's and Louis Legendre's book, Numerical Ecology, referred to these numbers. If you've used Kanoko, especially the DOS version of Kanoko, these are the numbers that you have to put in for the different scalings. And I'll show you in a second, there are simpler ways that we can now do this in vegan. But the idea here is that if it's scaling 1, we focus on the sites. Scaling 2, we focus on the species. Scaling 3, we do symmetric scaling. If we have negative scores, we can get out, if we've done RDA like PCA, then we get correlation-based scores. So we could fit the ordination as though using the covariance matrix with scale equals false, so on the covariance matrix, but we can get back correlation-based scores if we use the negative values. If we've done correspondence analysis and we use the negative values for the scaling, then we get what's known as Hills scaling. And it's not the Hills scaling standard deviation units of things like DCA that you might be familiar with, but it's just a different kind of scaling that might come up, and I'm not going to talk about that at all here. Okay, and if you put scaling equals 0, then you get the raw scores, and those raw scores would be the sorts of scores that you would get back if you just did like a principal components analysis using PR comp and from the base R distribution. So no one can remember all of those numbers, and I can never remember them. So actually a couple of years ago, I went through and changed vegan so that it would accept these things. So now you can give it a textual name instead that makes a bit more sense. You can do scaling equals none, that gets scaling 0, scaling equals sites, scaling 1, and so on. Actually, I made a mistake there. It should be species is scaling 2. Sorry, I was doing a bit of copy and paste. And then if you want the negative scores and you've done an RDA, you can pass in correlation equals true to get the correlation-based scores. And if you've done CA with CCA, then if you want the Hill scaling, the negative versions of the scores, then you would pass Hill equals true. So scaling, correlation, and Hill combine to give what we had before with the single argument, but now hopefully you don't have to remember what 1, 2, 3, and so on means. Now, why I'm mentioning this is that when we come to plotting, if you change the scaling from the default that's set in the function when you plot or ask for the scores in some way, then you have to make sure that you keep applying or asking for the same scaling as you go along if you're doing any plotting or any analysis of the ordination scores. So you're going to get used to seeing scaling a lot as we go through the next bit. Okay. If you want to do your own analysis, right, if you don't want to do the plotting like we're doing in the next few slides, if you just want to get the scores out and do stuff with them, then you should use the scores function. Don't rummage around inside the objects that vegan's ordination functions return. A, because we might change the way that they are stored internally, okay? But B, you might not get back what you think you get back, and sometimes the scores are not stored in the way that you think they're stored, okay? So always use the scores function to extract the scores. And scores, you can give it choices, which is just the number of axes you want. So you can tell it which axes you want. Here I'm asking for the first 3. You use the display argument to choose the different scores that you want. You can have multiple kinds of scores. Here I'm just asking for the species scores, but if you wanted the site scores, you just put sites there instead for display. Here you have to set the scaling because what you have to apply the scaling when you extract them, okay? So the scaling is done here using the scaling function. So here I'm asking for the species scores and species scaling, and I want to be the negative scores from our PCA because I'm using correlation equals true, okay? These arguments apply whenever we're plotting any of the ordination scores. All of those functions have defaults. You have to be aware of them or set them explicitly if you don't know what the default is, okay? So to be safe, set them, right? So our basic ordination plot, we've seen this already. It's the plot method. You can pass in the choices to tell it which axes you want to plot. Obviously, we're plotting on a 2D surface, so you can only give it 2 axes. Here I'm showing how we plot axis 1 versus axis 3 of our correspondence analysis. And I'm doing the symmetric scaling. So I could pass in different things. If I only wanted to show the site scores, then I would set display equals sites. If I only wanted the species, I would set display equals species. Here, the default is to show them both, so concatenate site and species. You can use the text argument to control whether vegan plots these things as points or as the text. Here, because this is a relatively small data set, it's actually plotting them as text, even though there's over plotting. If you have a large data set, then you would end up with just a series of points. Okay, but you can control that using the type argument. Okay, and then there are other graphical parameters that, if you're familiar with base graphics, you can pass them in here, but they don't necessarily have the same effects as, because they would actually refer to one or both of the scores, right? So I'll show you how to build up your plots better later. Okay. So some distance-based methods now. Just have a look at some of the questions. So I think we're going to be running over by about 10 minutes or so, I think, at the moment. But let's go. Someone asked, is there any limitation between the number of species and the number of sites that are going to be analyzed? No, the vegan can sort of take whatever, as long as you've got enough memory to store the objects and do the computations. But yeah, it doesn't matter. And you can have many more species than you have sites or samples, okay? If you're doing presence-absence analysis, should you scale the site as you can't scale presence-absences? In that case, if you've got presence-absence data, then you wouldn't need to be doing something like PCA. That isn't really for that kind of data. Presence-absence will work fine with correspondence analysis. Or you can use one of the distance-based methods that we're going to mention now and just use one of the binary coefficients that that I didn't mention, but I said how I put the slide in. Okay. So distance-based methods. Let's have a look at the first one, which is this thing called principal coordinates analysis. This is metric multidimensional scaling. So this is not NMDS, it's the metric version. Okay. And its acronym is PCOA, or sometimes PCO, or sometimes MDS, depending on the literature. And what this is actually very similar to principal components analysis. But what it's trying to do is trying to find a mapping to Euclidean space, so normal Cartesian coordinates that we have. So a Euclidean space, a mapping in Euclidean space of our n objects using the n by n matrix of dissimilarities. So important here, rather than giving it the raw information, our raw matrix or data frame of observations, we have to convert them into a dissimilarity matrix first, using VegDist or something like that. And then we use principal coordinates to find a low dimensional mapping. So PCO, principal coordinates, is an eigendecomposition like PCA. It's just done on a transformation of the dissimilarity matrix. So that first axis finds the best one-dimensional mapping of the dissimilarities. And then you find the second axis, just like we did with principal components, it finds then with two axes, that's the best two-dimensional metric or linear mapping that we can get of those dissimilarities. Each axis is orthogonal to the other axes, and we can keep extracting extra axes out of the ordination up until we reach the limit, which is usually the number of the samples or species minus 1 first. Sorry, the number of sites minus 1, but there may be some issues when we have negative eigenvalues. So you can use any dissimilarity coefficient here. So these techniques are really adaptable. Any dissimilarity coefficient can work, but there's a big but, and we'll talk about that in a minute. If you were to do principal coordinates analysis of a Euclidean distance matrix of your data, then you'd get back a principal components analysis. You just don't get the species scores, right? Obviously, you get different ordinations, different mappings if you use different dissimilarities than the Euclidean one. And the idea here is that you could use something like Bray-Curtis or some other dissimilarity that you can't represent in correspondence analysis or in principal components analysis, so that you can actually get an ordination of the thing that you're most interested in, which would be the dissimilarity metric that you're representing the relationships between your sites in terms of. Okay, so the big but with principal coordinates is that not all dissimilarity coefficients can be represented in Euclidean space. So if our dissimilarity metric is metric, then we're okay usually, but there are some situations where you can still get into trouble even if your dissimilarity matrix is metric. If it's not metric, you'll get negative eigenvalues. And what these things correspond to is they correspond to distances in the imaginary plane, plane of imaginary numbers, not the plane of the real numbers. Okay, so the Euclidean coordinates you can represent coordinates in the real numbers in that coordinate system. If we get complex, if you have negative eigenvalues, if they're not metric, then you get distances in the complex plane as well with these imaginary numbers. And then we have this issue about how do we represent things, because the first few principles because they're ordered from high to low, the eigenvalues. If you get negative eigenvalues, they might be important components, but they're way down at the other end and they won't get plotted, right? Because they're negative, because we only focus on the high values. And so this can cause a problem if you're not careful. We can look at the distortion by, for example, if we sum up the absolute values of the negative eigenvalues and divide them by the sum of all eigenvalues, then that relationship there will tell you the degree of distortion, i.e. how bad the non-metric part is of this, or the imaginary part. There are ways to correct this. One way is to, you could try and square root transform the dissimilarities, and that can sometimes work. So you would just apply the square root function to your dissimilarities first. Other ways involve actually modifying the dissimilarities as you're calculating principal coordinates. And there are two methods. One's is Lingo's and one's is Caillere's. And they apply different transformations. So in Lingo's, we work on the square of the dissimilarities, and then we add on 2 times some constant C1. And if we're in the Caillere's method, then we work in the original dissimilarities and we add on a constant C2. Okay, and we don't touch the diagonal values, so we look at all in the dissimilarity matrix. We're just working on the off-diagonal values. And C1 is just the maximum of the absolute values of the negative eigenvalues. That can correct the problem. And the Caillere's method is a bit more complicated, but it also it's based on some matrix that's actually formed when we do the PCA internally, and you can apply the correction there, and then that will get rid of the negative eigenvalues by adding on some constant. Now, you don't necessarily need to understand the differences, but they are modifying the distances before you calculate before you actually do calculate principal coordinates. So they're going to change things, and they do have some effects, right? But they're easy to apply. So the default, let's have a look at an example of this. The default dissimilarity in VegDist is the Bray-Curtis. We saw that earlier. And so I'm going to look at now doing a principal coordinates analysis of the lichen data, but I'm going to transform the lichen data. I'm going to calculate the Bray-Curtis distance from the lichen data using VegDist. So that's the default. So that's up here. Okay. And then if you do I equals true, you just get back a ton of information. So I'm just going to leave that I equals true. Right? And the PCO function in vegan is actually called W command scale. This is for weighted command scale. I can't remember why it's command scale, but it's multidimensional scaling. Can't remember what the C stands for. It's a weighted version. If you don't pass in any weights, then you get back principal coordinates analysis, right? And I'm just doing this so I just work in vegan without having to do something else, okay? And so if we do that analysis, you just run it and you get back an object which you can plot. It's just like another ordination axis, another ordination technique. But if we look at the eigenvalues, you'll see that quite a few of these eigenvalues are negative, right? And that's because Bray-Curtis isn't metric, right? And so you can't represent Bray-Curtis distances in a Euclidean space, and we get these imaginary eigenvalues or imaginary axes here. All right. If we then want to apply one of the corrections, here we use the add function and we give it the name. Here I'm doing the Lingo's correction. Now, when we do our and we run this again, we get and look at the eigenvalues. Now we see that all of the eigenvalues, in fact, none of them are 0 or lower. There's no negative eigenvalues. But there is, if you were to count these up, you'd actually find that there is one fewer dimension than before. And so this is the thing, you do actually lose some of the dimensions, right? It's not this correction is not without issues, but it does change some of these dimensions. But now we don't have any of these negative values. So we've accounted for that, got rid of that imaginary bit. Okay, they are really a correction to things, but you kind of have to do them, or in fact, actually, you don't have to do them. You could just ignore them, but you do have to be a bit careful about if you do have large negative eigenvalues, then it does suggest that the mapping that you're getting from the PCO is going to be distorted. It's not going to be a very good mapping because you're ignoring a lot of the information in that dissimilarity. Okay, so principal coordinates analysis, we've done that. I'm just going to show you this the plot of these things, and here I've forgotten to correct the negative eigenvalues in the code up here. I have to see if that's the default. Okay, but then we can plot it like any other thing. So when we plot, we just get a plot of the samples because there's no more information. But we could extract the scores from our PCO. So I'm extracting the information on the first for the samples, the sites on the first two axes. I'm extracting that here, and then I'm calculating weighted average scores. Now, these are not weighted average scores. They're not species optima in the sense of the correspondence analysis, and they're certainly not directions of increasing abundance like they would be in principal components analysis. But it is a way, using this WA scores function, to just add some of the species information to the plot. So what I'm actually doing here is I'm taking the axis scores and I'm using the abundances of the species as the weights. So I'm finding the red points now are the weighted average of value. So it's a weighted average of the site scores. So it's a weighted average of all of the sites that this species occurs in, and the weights are given by the abundances. So we give more weight, this point will be pulled towards those sites where it is most abundant. So this is just a way to add things to the principal coordinates analysis plot. And it's very similar to how NMDS works in a minute, which is what we're going to talk about next. Okay. So NMDS, it like principal coordinates analysis finds a low dimensional mapping that best preserves, but it preserves as best as possible the rank order of the original dissimilarities. PCO was trying to find the best mapping of the actual dissimilarities. NMDS says, I'm going to ignore the actual values. I'm just going to try and map the rank orders of the dissimilarities. So what I'm going to have is try and have a mapping where the largest distance, the largest dissimilarity between any two samples, I'm going to try and make that mapping so that it is the largest distance in my map. Yeah, but I'm not going to make it, let's say that largest distance was twice as large as the next largest distance. In NMDS, I don't need to make it sit twice as far away from the data point as an observation that's only half the distance away, because I'm only going to work in the rank orders. It just needs to be a little bit further away, right? In PCO, it would try and represent those actual absolute dissimilarities. And so NMDS can actually find better solutions because it's not restricted to actually be working in those original dissimilarities. So we want to find a usually two-dimensional, but doesn't have to be, a two-dimensional solution that minimizes the stress. It's a measure of, and stress is a measure of how well the NMDS mapping fits or represents the original dissimilarities. And stress is just the sum of squared residuals of some monotonic regression between the distances in NMDS space and the distances, the original distances. This nonlinear regression and the dissimilarities, that metrics that you're using allow this technique to represent all kinds of data. It can be nonlinear relationships, linear relationships. Using the right dissimilarity coefficients, you can encode all sorts of information in here. Now, this has its problems though. The algorithm is just an iterative solution. There is no guarantee that it will converge on a good solution. And you have to solve it separately for different dimensions. So when we've done PCA, CA, and PCO, you get all of the axes in one go. With NMDS, if you want a two-dimensional solution, you fit that. Then if you want to see what the third dimension looks like, there isn't a third dimension. You have to go back and start again and fit a three-dimensional solution. Okay. So there are some complications to using this, but thankfully the vegan allows you to sort of hide some of this complexity for you. Okay. So in NMDS, we use some appropriate dissimilarity metric that gives a good gradient separation. You can look at how well the different dissimilarity metrics available in vegan sort of separate or explain your data using the rank index function. And things like Bray-Curtis for abundances, the Yacob or Kulczynski for binary data are pretty good ones that tend to have good good separation of the observations along gradients. You might want to standardize the species to equal maxima and then sites to have an equal total. That's this Wisconsin transformation. With NMDS, I mean, these are all recommendations that come from Peter Minchin and other people that have looked and done a lot of work on NMDS. So what they recommend, because this is an iterative algorithm, you might want to do many random starts. And if you end up with several solutions that look the same, then you probably got to a global solution, a good solution. If you do many random starts and they're all different, it suggests that you're getting stuck in local optima, and you might want to keep trying to find some matching solutions to see if you find a global one. Okay. We only conclude that we've reached a good solution if the lowest stress solutions are similar enough to one another, and we assess that through a thing called Procrustes rotation. It just means that if we twist and scale and whatever things together, we can measure how similar configurations are by rotating and stretching and translating one thing relative to another. Okay, so we can actually compare the solutions that come from different random starts. You could, if you want to know how many dimensions you have, you could fit NMDS for one dimension, then two, then three, and look to see where you stop gaining anything by having the extra complexity. And then we rotate the solution usually to principal components, and then we might scale axes in terms of half change units. So in half change units, that's where samples that are separated by a distance of 1, that corresponds to an average of 50% turnover. So by scaling the axes in half change units, we get some idea about how much compositional change goes on the axes. Okay. So NMDS is implemented in vegan in a number of different functions, but what those things that I just mentioned are implemented in the meta MDS wrapper itself. So meta MDS is a wrapper function that calls lots of other functions that just does everything I just described, but it will turn on and off certain things depending on some heuristics. So you might want to look at the arguments to decide whether you should be doing some of those things. For example, the automatic transformations using Wisconsin function, you don't want to apply that if you're going to do NMDS of environmental data. So do look at the help for meta MDS to decide what is appropriate for the particular data you're going to be doing. Okay. And so, but you don't, and with meta MDS, you don't even have to provide a dissimilarity matrix. It will convert your data to dissimilarities, and it will just use whatever VegDis default is. So it'll use Bray-Curtis. So here I'm going to use the classic June meadow data. I'm setting a random seed because this is iterative, and then I'm going to use the meta MDS that's going to turn everything on. And just because it's going to print a whole load of stuff to the screen, I'm turning off the trace here for my slides, but you would want to keep the default as trace equals true so you can see what it's doing and where it's finding solutions that are good. Okay? And so then we're printing this and we get some solution. It tells us that we use Bray-Curtis distances, what the stress measure was, and it said it found 2 convergent solutions after 20 tries. So it will do 20 random starts, and then it found 2 solutions that were very similar to one another. So it then stopped and it declared convergence. And then it's telling us about some of the transformations that were done. Okay, and as I said, these are automatic transformations that happen, and if you don't have species abundance data, you probably don't want them, so you need to turn them off. Okay. Right, now what happens if you don't have something as good as this, that it might tell you it didn't find any convergent solutions? Or what do you do? Well, because we saved it in this thing called sol, we can then start the algorithm off from the previous best solution and see if it can do some more random starts and see if it finds a solution that was similar to the best solution from the previous set. All right? So now what I'm showing, we can use this previous.best argument to pass in a previous fit of NMDS, and then it will just run another 20 and see. Okay? And if you are having problems getting this to converge with 20, then there is an argument called try max. You can make that larger and it will just do more and more random starts. Okay. The only issue with that is obviously it takes a lot more time to do the computations, but computers are getting fast. So unless you've got massive numbers of observations and large numbers of observations, then you can do a large number of random starts in a few seconds. Right? So try max, you can up that. Okay. And so here it says it's found 2 convergent solutions after 40 tries because each one did 20. So there are 2 sets of 20 tries here. Okay. So we can do a default plot. That's what's shown here on the left using plot sol. Okay. And then we can also look at how well our solution maps the underlying original dissimilarities. Okay. So remember now, what I'm talking about is the dissimilarities that I'm talking about on the MDS are the distances between these points. So we can take the Euclidean distance between all of the points in this 2-dimensional mapping, and that represents the distances in MDS. And then over here, we are comparing those distances with the observed dissimilarities. So the observed dissimilarities are down here. And the red line is actually the monotonic regression that's actually done to sort of find the configuration of points in here that has this best fit of this monotonic line in here. Okay, and then we get 2 measures of the fit. We have a non-metric version. The non-metric version is just based on the stress. Okay, so it's measured now as an R squared, so it's now 1 minus that. It's actually 1 minus S squared, I think, is actually how it's computed. Okay, and then we get a linear R squared. So this would be if we put a linear relationship between these 2 distances, what is the R squared? So if we just fitted a straight line through here, what is the correlation essentially between them? All right, and that's what they're doing here. So here you want these R squareds to be high, but if you're looking at stress, you want stress to be low. All right. So if we're checking, the one final thing is you want to know how many, maybe how many dimensions. Most people will do this and they'll just do 2 because that's the easiest thing to map. But you can, and I'm showing here some code that will show you how to look at the different dimensionalities. So I'm showing solutions with dimensions 1, 2, 3, and so on up to 10 dimensions. And I'm plotting the stress value of each of those solutions. Okay. So what I'm doing in the first line, I'm just saying I want to do dimensions 1 through 10. I'm setting up something to hold a stress. So I'm going to have the stress. It's going to get put in here for each of my 10 models. I do the dissimilarity that the meta MDS function would automatically apply. And this will do any of the transformations and things like that. So that's a little function here that will do some of what meta MDS is doing. Okay. This is random again, so I'm setting the seed. Okay, and now I'm going to do a loop. I'm just going to loop, and each time I'm going to fit, I'm going to get the MDS, and it's going to do random starts, but I'm going to get the random starts by doing this thing here. So this is just going to do random starts for me. Meta MDS combines both of these plus some other things, but because I'm breaking this out, I'm only applying the transformation once. Then I want to do the random starts for each k here. I've just used these sort of other functions to do it. And then I'm just storing the stress. Right? And then I'm just plotting it. And we see here you want to stop roughly when there's an elbow or a change in slope, because the extra information that you're getting, the extra fit from the mapping, isn't adding much as you add more dimensions. And so it suggests here that 2 dimensions is probably all that you really need for these data. We can look at a measure of the goodness of fit for each of our observations, how well they fit in the mapping, using this function called goodness. And if you calculate that, basically the goodness statistics, or these G values, they are defined in such a way that if we were to sum up the square of these g values, then that would give us the stress squared. And the other lines in here, I'm just showing you that this is true, okay? That if you were to sum up those g squared, you get this number, and this is the stress squared in our solution for our 2 dimensions, okay? And I'm just showing you that they are equal, all right? Okay. So that's what's going on here, and it's just basically saying and the larger the value here, the more that observation contributes to the stress, so the poorer the fit for that particular observation, right? And the smaller the number, the better the fit, right? So you can actually go in and evaluate this a bit more. Okay. So supplementary data, what do you do if you've got these other environmental variables and you want to apply them? Then we really have 2 main functions. I mean, there are lots of things that you can do, but vegan provide 2 main functions to do this. One involves fitting straight lines and planes, so saying that you have linear relationships between the ordination axes or the mapping and your environment. Or we have ordisurf, which says that there are nonlinear relationships between these things. Okay, and we're going to look at both of these first. Now, so when we're doing vector fitting, vector fitting, we have nfit. It fits vectors using this regression here. So there's no intercept in this model, and all it's saying is that this is my environmental variable that I want to fit the vector for, and I'm saying I want to predict the values of the environment at my samples or my sites, and I'm going to do that as some linear combination of the axis scores. So we might just have the first 2 axes, in which case we can ignore the rest of this over here. Okay, but it works in as many dimensions as you want, all right? But typically we're just doing it on a 2-dimensional plot, so you'll just have this bit here, all right? And what this does is it's actually finding a direction in the ordination space that finds the maximum sort of correlation with the axis scores. That's what we're doing. But another way of thinking about it is, can I predict the environment from my ordination scores? Usually the first 2, right? And you don't have to do it as a single environmental variable at a time. You can pass in a matrix of environmental variables and it just will work. It'll do all these calculations for you for each environmental variable separately. So there's no intercept, remember, in this model. So internally, these are all being centered. Okay. And for categorical data, nfit doesn't do what I've just said here. What it does is just finds averages of the scores for each level of the categorical variable. Okay. So let's have a quick look at that. What I'm showing here then is nfit on our original principal components analysis that we did earlier. And I'm going to now use the chemistry data and I'm going to project vectors in for those chemistry variables. So I'm going to look for the correlations essentially between the environmental variables and the first 2 principal components that we extracted earlier. Okay. I'm telling it to use the symmetric scores. If you wanted to have if you were doing plots with the scaling is with sites or species, remember to change it here, okay, and what have you. So you have to remember to pass in those extra things. And we're doing a permutation test, and this is just randomly shuffling things. If you want to find out more about permutation tests and how to do not just random shuffling, then come along on Thursday. And you can pass in, so we do a formula here. On the left-hand side, we pass in the ordination object, and on the right-hand side, we do a dot, and that dot means give me everything that's in the data object. So this will just do it for every variable in varchem. Or alternatively, you can just pass in the ordination and the data frame that you want to use for the vector fitting. Okay. The main things though, you have to tell it which ordination axes you want. So if you're going to plot these in the first 2 axes, you need to tell it that you just want to use the first 2 axes here. And you have to remember any scaling, correlation, hill arguments have to go in. All right. And then we get this output. So the values in PC1, PC2, those are direction cosines. So they're essentially like the put together. If you take PC1 and PC2 here, they are the directions in the ordination space for the vector for that variable. And these are all standardized, so they have unit length. So you can essentially compare them between variables because the arrows have unit length. R squared is a measure of the correlation between the environmental variable and where it projects onto that vector. Okay? So if there's a strong correlation between the values of the environment and where those values project onto this vector that we've put into the ordination space, then that suggests that there's a strong correlation there. If there's a weak correlation between that projection, then it suggests that there's a weak correlation between the axis scores and the environmental variable. The important thing is it's not a correlation between the axes, it's a correlation with the values that we get from the vector and the data, right? Because it's a single value, yet we have two axis scores here, yeah? So two components of the axis score. It could be three, right? But we get one measure of the correlation. And then in the P column here, the PR column, this is the p-value of that permutation test. So you can see that in this instance, we only really have sort of a good relationships with the bare soil measure and to a lesser extent with iron, manganese and the humus layer. Okay. And we'll talk more about what the permutation tests are later, but here it's just doing randomly shuffling the environmental variables and then re-projecting the vectors in there, and that represents the null distribution. Okay, so you can plot that, but we have a bit of a bug, so we'll ignore that one, and I should go and fix that. If you want to, you can add them. So by default, the plot method would add them to a plot. And so what I'm showing here then is a plot of our PCA. I'm just displaying the sites and I'm doing the scaling equals symmetric. Because I used scaling equals symmetric before when I did MFit, I need to display it using the same scaling here, all right? I'm adding on the points. So I'm actually adding on points for my samples. So I'm just showing how you build up the layers by adding points. Again, we have to pass in the same scaling information. And then I use the plot method, so to plot the vectors in here. So we can see now, when we plot them, those coordinates were giving, where I said were unit length arrows. So all these arrows would have had the same length. But now when we plot them, we're actually scaling them by the R² value. So bare soil had the highest R² value, I think. So it has the longest arrow here. So the lengths of the arrows represent how strong the correlation is with the ordination configuration. So the longer the arrows, the more important these points were. The stronger the relationship with the ordination axis. Okay? But they point in increasing abundance. So bare soil increases as linearly across this line. Right? Now that might not be a good representation of how bare soil varies, or some other variables vary across this surface, but we've only fitted a linear model. If there is a nonlinear relationship between these variables and the underlying ordination configuration, then NFit won't capture that. And that's where ordisurf comes in. So ordisurf uses GANs, uses smooth functions instead of fitting lines and planes. So what ordisurf is doing is it's saying, I want to fit my environmental variable as a smooth function that we're going to estimate from the data of my two axis scores. Now you can only do two axis scores here. We haven't written the function to do higher dimensions. It will be possible, but it gets complicated to write the GAM equations, the formulas out. Okay, so it's just for 2 dimensions, all right? But this gives you actually a lot of functionality. And the way ordisurf works is it actually uses the MGCV package under the hood to do the smoothing to fit the surface, all right? And so you have a lot of flexibility to use things from the GAM package, from the MGCV package, sorry, to fit this stuff. So here I'm just showing an example. This is, I'm looking at the calcium. Now calcium didn't have a particularly strong correlation with the ordination axis. And that's partly perhaps because the relationship with these ordinations is not linear, right? We seem to have sort of, and I can't really read everything here, but it looks like it's increasing this way and then decreasing as you go down here, all right? And so because that's non-linear, the linear vector can't really do a good job of capturing that one. So this is where the non-linear version is good. right? And so in the code here, what I'm doing is I'm just saying I want an isotropic smooth, so I want the same smoothing in both X and Y here, both principal components. I'm going to use 10 knots, that's quite a flexible surface, but the way we do these is that it'll get rid of any extra wiggliness, and so it will only fit something that's as smooth as it really needs to be, or as wiggly as it needs to be. That's how GAMs work in MGCV. And then when you plot this function, which I'm not showing, but you do, it actually, because when you run the function, it also generates a plot, right? So I'm just saving the output so we can go and look at it afterwards. But by default, you get the plot as well, okay? And this shows the nonlinear surface, yeah. And you can do summary on that object that we saved from AudiSurf. And when you do that, you actually get the GAM model. You print, if you do summary, you get the GAM summary. If you print it, you get the GAM outputs. And you can actually see here that this regression surface is actually statistically significant. Although, whether we're actually meeting the assumptions of the method or not need to be checked. Okay. So I've got a few more things about just doing some plotting, and then we will finish for today. Just going to have a look and see if there are some more things. Okay, so non-metric dimensional scaling. What do we mean by rank order? What I mean by that is in principal coordinates, the dissimilarities have to be, the mapping has to be exact, right? So if the distance between 2 points is say 5, then, and there's a distance between 2 other points is like 2.5, right? Then I have to make sure in my low dimensional mapping, I have to try and best represent my points so that the distance between the first 2 is twice the distance between the second 2, right? So the distances in the ordination represent the actual dissimilarity values as best as possible, right? Now they're not going to do it perfectly unless you use all possible principal coordinates, but they're going to do, that's what they're trying to do. Even in 2 dimensions, it's going to best represent that mapping of the actual dissimilarities. In NMDS just says, it just says, okay, I don't care that the distance between the first 2 points is twice the distance between the second 2 points. All I want to do is make sure that the first 2 points lie further away in NMDS space than the second 2 points, because the second 2 points were closer, right, than the first 2 points, pair of points. So that's what I mean by rank order. It just tries to get the ranks. So the biggest distance in the actual dissimilarities should be the biggest distance on the NMDS plot. The smallest distance between pairs of observations should be the smallest distance on the NMDS plot. Okay. I'm not sure how easy it is to explain how much variation there is by each NMDS axis. Ideally, you wouldn't really think about these as separate axes like you would in principal components because they're not orthogonal, and also we rotate the thing. I think you're better off thinking about how well the 2-dimensional solution fits the actual dissimilarities. Okay, so let's go and do some plotting bits now. So as you've seen, ordination diagrams can get messy, and the default functions plot and biplot that we provide to you are really only designed with Vegan to get a quick plot of the results just so you can see what's going on. Inevitably, there's going to be overplotting and there's going to be a mess. So how do we get better plots, essentially? Okay. So one of the most useful functions is a thing called ordi_point label. So it's going to add points and labels to the plots. Before, the plot was just representing it as points or text labels, one or the other, right? Here we're going to get points and a label, so we can see the points and how they lie in relationship to one another. It's easier to interpret where the points are, especially if you've got long labels. But we're also going to get a label so we can identify what's in each plot. Okay. Now this actually uses an iterative algorithm, and it tries to make sure that the points and the labels don't overlap the points, and the labels don't overlap one another. All right. So it's iterative, so set the seed if you want to make it reproducible. And what I'm doing here then is, by default, it will just create a plot. Yeah. I'll show you in a second how you can add it to an existing plot if you want. But here we set the seed, we use ordi point label, you give it the ordination, and then you need to tell it how you want, what scores you want to work on, and what scaling to use. Now I'm just using symmetric just to sort of show you that we can change the scaling. It's important though from now on that you remember what scaling is happening, is being used throughout, because every time you add something to a plot, you need to make sure that it's been done on the same scaling, right? Otherwise they won't match up. Okay, so iteratively, this one has done a pretty good job. We've actually managed to label everything, I think. We haven't got any labels overlapping, and you just have to be a bit careful about interpreting where number 9 is, for example. But when you look number 10 in here, you can see where they sort of map out. So if you've got a relatively clean diagram like this, you can get a reasonable plot this way. Okay. You can add things to the plot. So you can add ordi point label to an existing plot. So to get better plots in vegan, usually what you have to do is you have to set up the canvas first by using type equals n. So this sets up the space you want to do the plotting in. Okay. Here again, I'm just showing the sites and I'm doing symmetric scaling. Okay. Then you can add in the points that you want. So I'm adding in, again, I'm sites and I'm doing symmetric scaling. But now I can start changing the plotting characters. So now I get the blue points on here, right? And then I can label them. So I can do set.seed, okay? And I can add the labels to these points, right? And that's what I'm doing here. So it's adding the labels to the points already there. And in this instance, because it's relatively easy, we actually get the same, we do get the same solution. Did I set the same seed? Okay, yeah. So we get the same solution because I set the same seed. If you didn't set the same seed each time, you would get slightly different configurations, okay? And it's a stochastic algorithm that's used. So you run it twice, you'll get a slightly different positions for the labels. And you can do that for the species. So here I'm showing exactly the same thing, but now I've just decided to display the species scores from the same ordination. I'm using symmetric scaling again, but I'm only showing the species. Okay? We're doing exactly the same thing though, adding in the points and the labels separately by different separate calls. Okay? The only thing here is, as you can see, this is slightly less successful. The labels are a little long and it doesn't quite get them in the ordination axes, given the axis limits that I've got set here. And they perhaps overlap a little bit with some of the points in here, all right? So as things get more complicated and as you have longer and longer labels, then there's less and less room for the algorithm to find a good solution, all right, and to stop them overplotting, okay? And the only solution to that actually would be to go in and manually edit these plots. And we do have a function called orditk-plot, which will use a little GUI in R to do that. Or the other thing you could do is you could just export this to Illustrator or Inkscape or something like that, and then tweak it, all right? But this will get you most of the way, and then you want to fix the few bits that haven't worked. And really, you know, ultimately, you're only going to get a very, very good ordination diagram by hand tweaking some of this, right? And as you see here, and this now, if we put both the species and the sites together on the same plot, this is a much harder problem. Yeah, the species, because we're using symmetric scaling here, are all clumped up a bit. The algorithm isn't going to do a perfect job. In fact, it's going to do a far from perfect job here. And it isn't going to find a space for all of these long labels. Now, I don't have time to go into it today because we've already run over by a bit. Well, quite a bit actually. But there are ways you can choose certain species to label or certain sites using the select argument, all right? But again, if you want to do something like this, you're not, with a large number of species and sites, you aren't going to be able to get a clean diagram. So you need to think about what you show and how you show it, right? Vegan provides all of the tools, but you have to then do a lot of work. And so you can see here, there's many lines of code just to try and get a simple plot like this that just has a couple of different colors and some labels on it, all right? This is one of the strengths of base plotting, but it's also one of the weaknesses in that sense, right? They've got a lot of work, but you have ultimate control, okay? And when I say that, you are in control of everything. This plot here would be trivial to create in ggplot, right? But because we're using, trying to get a legend and do colors, This is a little bit more complicated in base graphics, but you can do it, and I'm going to show you how you can do these things in base graphics, because that's without doing things by hand and really getting into the nitty-gritty of how you do of a lot of coding, it is actually quite hard to turn all of this stuff into a good ggplot. Okay, so what we're doing here is I'm going to use the June meadow data set again and some environmental data that come with it. I have 4 levels. I'm going to look at the management. So I'm going to do a PCA of the June species data, but I'm transforming it using the Hellinger transformation, so it's suitable for species. All right. I'm going to look at how the management of these June meadows varies. And so the different management values are going to be colored red, blue, orange, or gray. I want to show the sites, and I want to do symmetric scaling just to show you that changing the scaling. Okay, so that's how we fitted the ordination. And then we have to plot it. So the first layer here, the first plot, is just setting up. By doing type equals n, we just set up the axes, but it just gives a blank canvas on which to work. Okay, so the axes will be there, but there'll be no points. Then what I'm doing here is I'm indexing my color vector with the management vector. All right. So management takes values 1, 2, 3, and 4, underlying, that's what the factor does. And so that then indexes, if it's a value 2, we get back blue. And if the next value is 1, we get back red, and so on. So now I've got a vector of colors that maps directly to the management values, all right, which we then use to plot. Okay. And then I need to add a legend. So here I'm extracting the levels of the factor, and then I create the legend by hand, right? Mapping the colors to the levels. And because I've done it this way, because I used the vector to do the indexing, to map my factor to the color vector, I know it's going to be in the right order when I use the levels down here to set the labels. Okay. Now, if you know ggplot, you'll know that if you could get the data in a nice format, all that legend, all the color stuff would be really easy to do, all right? But it's just not as easy with base graphics. You have full control, but that means you have to do everything, all right? So I'm going to look at a couple more utility functions, just some of the things that you can put on the plots. And I'm not going to go through the code in much detail because it's very similar, but I just want to show you the kinds of things that Vegan allows you to add to your plots just to sort of help interpret them. The first one here is using ordi-hull. Hulls, or convex hulls, just draw a polygon around the sets of the most extreme sets of points in your in each group. So if you give it a group, it will put a polygon around the observations in each group, right? So that hull contains all of the observations in this particular group, which is the nature management and so on. And then I'm using ordi spider to put these little spider diagrams on. And that then is just joining up the centroid, so the center of the groups, that's the group average. And then we see how each of the points varies from the group centroid. Right? And in this instance, you can think of these about the spread then is a measure of the dispersion. So there's a lot more variability in terms of the nature management. And I forget what SF is, but some form of farming. And there's more variation in those than there is in the other two groups, for example, just in terms of the spread around the group centroid. But we're doing here, we can color things, we can build up the plots in layer. But the key thing to remember is that we're using the scaling and the display arguments where necessary to make sure that we're applying the same scaling to the scores throughout. If you don't like the hulls, you can add on ellipses. And so ordi ellipse draws data, sort of ellipsoid hulls. And ellipsoid hulls are these ones here. So this is an ellipse that goes through all of the extreme points for that data set, or for that group of points, all right? And the inner one here is drawn as a standard error of the centroid. So this is how uncertain we are about the centroid of each group. And so that can be an idea about how significantly different these things are. These things overlap, which suggests that these two groups have very similar species composition, and in terms of the farming itself doesn't seem to have be related to a difference in the species composition here. There's perhaps more of a difference between this farming type and these two, and this one here, the nature management management type, is quite different. Yeah, there does seem to be. And I think if we're drawing here just one standard error, I think if we drew to more standard errors, these things would all overlap. But this one is still perhaps different. So that suggests perhaps here that there is an effect of the management type on the data. So this is on the species composition. So this colored inner ellipsoid is actually a kind of a measure of the standard error of this centroid as shown in 2 dimensions. Okay, so finally, before we wrap up, is there any hope that we might be able to do some of this with ggplot? Well, yes and no. I've been writing a package called ggvegan for a while. It's still in development, and it's kind of stalled a little bit just because I've been doing other things with my job and what have you. But ggplot does, the idea about ggvegan is that it's going to provide essentially a couple of things. One of them is it's going to provide this autoplot methods. For various reasons, we can't write ggplot here. We have to use autoplot. Okay, so we don't confuse it with the plot method in vegan, and ggplot isn't generic. So, but we are trying to provide default plotting methods for each of the objects in vegan, each of the different functions. So the ordination ones are sort of covered, and here I'm just showing you can just get the a plot of the PCA on the June data that we just did, just by using autoplot, and we get this. Okay, again, this is just going to be like the plot method. It's just going to use ggplot objects. It's just going to give you a quick and dirty plot. You'll want to build up your plot from other layers. And so the other thing that ggvegan is trying to do is to give you back fortify methods. Fortify is just a way of turning an object into something that ggplot can plot. Okay, and I think Hadley and people are now going away. They're not quite liking this fortify idea. And so in future, maybe ggvegan will return tidy objects. So it'll work like the tidy package. Okay, rather than like the broom package. Sorry, there it will create tidy representations of things that could be plotted. But Fortify isn't going to go anywhere as far as I'm concerned. So what Fortify does is it takes your ordination object from the vegan created, and then it creates something that we can actually use to plot in ggvegan. So essentially what it's doing is, for the ordination methods, it's extracting the axis scores. Here I just asked for the first 2 axes. It's returning information about the labels, so you could use this column here to put a label on the plot. And then it's also returning an information, so this is a vector of the different scores. And by default, the species come first, and then there's also the site scores are beneath it. So in this case, if I just want to show the site scores, I need to filter the site scores out. So I just use the filter dplyr function to filter out and just take the site scores from this object. And then you can use ggplot and anything you know about ggplot to create your own ordination diagram as you go along. The key thing about this is in ggplot, you have to set coord underscore fixed. If you don't set coord underscore fixed, your ordination diagram is going to look wrong and you can't really interpret it properly. And a lot of people, and even some packages for a time, had forgotten about this. All right, so just be careful. This just makes sure that the scaling on this axis is the same scaling on this axis. And now it means that we can interpret the Euclidean distances on these plots in the same way that we would do with all of the plot functions from vegan. Okay. So if you know ggvegan, if you know ggplot and wanted to get involved in helping do some of this stuff, then ggvegan is on GitHub, and help would be appreciated for this because it's kind of languished a bit. Okay. So I've finished now. Apologies for running over. I kind of spent a little bit too much time doing some of the diversity stuff at the beginning and the dissimilarities. Thank you for your attention today. I'd just like to thank NSERC. NSERC funds my lab. They're the funding agency in Canada. I also think we owe a great deal of gratitude to especially Jari Oksanen, who has put many, many years and many, many hours into developing vegan. Jari is the main author of the package, And Peter and I maintain the package with Yari now. Yari's just retired, but he's still just as active as either Peter or I in doing stuff in the package. And he's written this great tool that we can all use. So thanks, Yari, and thanks, Peter, as well, for helping us maintain this stuff. And to all the authors of Vegan, I've just mentioned the maintainers here, but there are a number of other people that have contributed code, and thanks to them. If you want the slides, remember, you can do whatever you want with these slides. They're released under a Creative Commons license. The thing is here, and the sources, do what you want with them. They're on GitHub. You should have the link. Okay. If there's some people around still, I will answer some of the questions from the Google Doc. So I'll hang around. And I just want to draw attention again to the fact that I did the webinars for free. I understand that... and the same with the one on Thursday. Times are difficult and many people have lost opportunities to do training. So that's why I've put these things on. But if you are able to, I would really appreciate it if you are financially able, if you could make a donation to the University of Regina Student Emergency Fund, which helps out. I know many students will be in difficulty, but this fund is, we can't do any fundraising activities or many funding raising activities at the moment during lockdown. And so the fund is now gone just when the students need the help the most. And so if you are able to make a donation, no pressure, I don't get to know what's going on there. But if you are able to, I would really appreciate that. And so you would have had information about that on the GitHub page or in your email. Okay. So let's have a look at some practical tips then. So the first question here is, for the ellipsoid hulls and the standard error ellipses, are the ellipses the shaded or the non-shaded ellipses? Okay, so let's go back to that. So this is in here. Okay, so the ellipsoid hull is this one, the non-shaded, so the non-filled one. Okay, that's this one here. And just like the convex hull, because the convex hull kind of goes, it's the convex polygon that encloses all of the points, right? The same is true of this ellipsoid hull. It's an ellipsoid that contains all of the points, right? So there are no other points that lie outside of this ellipsoid for this particular group. The standard error ellipses are the ones that are drawn, that are shaded, okay? And the ellipsoid hull, and I didn't mention this when I went through it, that's given here, that's this first bit of code. That's where we do kind equals ehull. So kind equals ehull will get you this one, the unshaded one. And then the default hull is being drawn by the second call to order ellipse. And that will give you this standard error ellipse. And that's kind of a measure of the, as I said, the uncertainty of the centroid. Do you have any recommendations for how many or what level of rare species should be removed from the ordination diagram? I mean, ideally, I'm an ecologist and I love the rare species. I think they're important and tell us a lot about the environment. And but I also understand that you might be having difficulties plotting things and getting a clean plot. I think really what you should do in that instance is try not to remove them, but maybe you don't label them, for example. And so you can draw the points so we can see that there's a species there and what have you. And we can see how it relates to other things. We're not hiding anything from the user then, but you're not labeling it. Yeah? And there's an argument called select, I think, in many of these functions, where you can choose select which species or select which sites. And so you could maybe, and that you could pass in a vector of like true, false, or things like that, or I think a number to select which species you want. And when you're labeling, you can tell it just to label the ones that are most important to you. Okay. Yeah. So that would be my advice. I try not to leave things off. Okay. Because that can be, you might be hiding things from people. Okay. Are there ways to create a plot by trait matrices from species by plot and species by trait matrices? Okay, so that bit I don't know, and I will actually go back and have a look. I'm not that familiar with these sort of things that might come in the fourth corner or these other sort of other relationships, these other data sets. So I will have to go and look at vegan and get back to you on that one. So is there a quick way to relativize the species by plot matrix in vegan, i.e. relativize by each species max or relative by detections by year? Okay, so the second bit about relativizing species detections by year, that's unlikely to be available. I don't think anything in vegan will do that in DecoStand, okay? The relativize by each species match, yeah, DecoStand can do that. So DecoStand, it has an argument called margin, and margin 1 is the rows, margin 2 is the columns. So you'd want margin equals 2, and then you can use the method like max or something like that, I think it is, that would allow you to, if margin equals 2, it will normalize by the maximum values in the columns, right? So DecoStand has an option to do that, so go and look at that. How can you remove the center label of the ellipse and place it on a legend outside of the graph? Okay, so in the code, you'll see in here that Audi spider is only where I'm labeling. So those things only get put on if you do label equals true. And I think you can do the same in, so here, label equals true. You could do label equals true in here or in this one, all right? But if you leave it at the default or set label equals false, I think that's the default, then you won't get the center label at all right? Now, I find them useful to have that, but I think, yeah, again, you might want to have the label outside and just have a point for the centroid, okay? If you want a legend outside of the plot, then I can't explain that now, but you can put the legend outside, and you just have to do it in a similar way to how I did for this one here, but you wouldn't put it in the top right. You'd actually have to work out how to push it out over here, okay, outside the plot. And if you put it outside the plot over here, you have to turn off something called clipping, because otherwise it would be clipped to the box around the plot here. Okay. If I get a few minutes later this week, I will update the Google Doc and with an example if I do. No promises, but I will see. Do I have any way to create the Audi ellipse in ggplot? No, not at the moment, although there are ways that there are sort of packages that will allow you to provide the information that will create the at least some of the it will have a geom that will create some of those ellipses. I think it will just do standard error and data ellipses. I think that's my recollection. But we could use the underlying code is there, so it wouldn't actually be too hard for me or someone else to write a new geom that would do the same thing as the convex hull or the ellipsoid hull. But no, there isn't an easy way to just do it straight away. Okay? Not from the sort of vegan functions that calculate it anyway. Yeah, you'd have to do the calculations yourself or rely on what the geom provides. Okay. How is nfit different from a PCA biplot and a constrained ordination? Okay, so this gets back to something I talked about at the beginning, which is this relationship between unconstrained ordination and constrained ordination. So when we do the PCA, we just looked at the species information in the example here, but we could have looked at the environment, but what we did here was looked at the species information. So those arrows that are on there are just the variables, the species. There's no environment in that one, okay? So we can add environmental arrows, vectors, to that PCA biplot using nfit, but there's no other way, well, there's no way just from the PCA that you would have the environment in there as well as the species, okay? That's why PCA is an unconstrained one. You just have one matrix of variables that you want to ordinate, usually species, or it could be the environment, something else, but you don't have both of them. The constrained ordination allows you to have two matrices, and it says, I want to extract axes from the species data that I can explain with the environmental variables I have measured. So the axes you get out of that can only are axes that are explainable by the environment. they're not the best directions through the multivariate space. So they're not the directions that would maximize the separation of the sites, but they are the best directions that you can explain given some linear combination of the environmental data you've collected. So where NFIT differs is that if you do PCA first, PCA is going to give you back that unconstrained, those best directions through the species space, right? And then you use NFIT to relate the other variables that you've measured, maybe the environment or something like that. You use these other variables to relate them to the best axes, the best directions. So that's the difference. If you're coming, whoever asked that question, if you're coming to the advanced webinar on Thursday, I will talk a little bit more about that and can go into it a bit more when I show you what the constrained ordinations do. So if I add the MFIT scores to an NMDS, how can I interpret the length and the angle of each one? Okay, so when we put them on, and this is the same for any ordination plot, when you're putting NFIT arrows in, the length of the arrow is now scaled by the R squared that I mentioned. And so the longer the arrow, the stronger the correlation between the environmental variable, the thing that the arrow represents, and the ordination configuration in the 2 dimensions, right? So the longer the arrow, the stronger the correlation, okay? Because the angles are cosine directions, then you can interpret the angle as being a correlation between the 2 environmental vectors. So the angle between the arrows is a correlation between, is the correlation between them. But you have to remember, it's not the correlation between the two variables. It's the correlation between the 2 vectors on that plot. So another way of thinking, if the angles are very narrow, then it just says that the values of those 2 environmental variables change similarly in the same direction across the plot. That's really all that you can say. Okay. The length is perhaps the most important one, but the angle between them suggests that there is a correlation between those 2 variables and how they relate to the underlying ordination. Yeah. If I use Euclidean distance in a PCO, is it possible to use the same methods to graph the results of a PCA? Yeah, you can do. I think most of the underlying structure, it works the same. I'm pretty sure. I would have to get back to you, but I think it is. I think it works the same way. It has a scores method, and most of these functions that I just showed at the end to create the different kinds of plots and the hulls and stuff, they all work using the scores methods. And so if it has a scores method, which it does, then it should work the same way to extract the scores. Okay. Okay, well, thanks for the comments at the end there. I'm just going to flick back through and just see if there are any more things that jump out that I didn't get to. Okay. So I don't think so. Okay, so what I'm going to do, because it's almost 1 o'clock, we've gone over quite a bit. If you're still here, you've got some stamina. Thank you very much for paying attention and watching. I will get the video up on YouTube, the recording, just as soon as it's processed and available, and I will send a link to everybody. And if you are coming on Thursday, then I look forward to talking with you more, and I will try to stick to time a bit better. Okay, all right, thank you very much. Bye-bye.